Licenzianza, penso che da qui.
They wouldn't even engage in sex. Then they realized that if they can't.
Good afternoon, everyone. Good morning and good evening, all. And welcome to the 5G webinar. My name is Anita Natwati. I'm a training coordinator at Afralty, and we are really thrilled to have you join us today. I kindly request we give other participants 5 more minutes before we begin. Thank you.
Good afternoon, Anita.
Good afternoon, Mwenya. How are you?
I'm great to see you.
Great to see you too.
Yes.
Yeah, we are starting in a minute. I believe more people will be joining as we proceed.
Okay.
I can see our speakers are ready and our moderator also is very ready here.
Brilliant.
Oh, okay, thank you.
Thank you.
Okay, team, we now may start. I once again welcome you to our 5G webinar. And I take this opportunity to thank each one of you for taking your time to participate in our webinar. I can see we have our speakers ready and our moderator, Madam Kathy Kagwira, is here. Our speakers are Mr. Mwenya Mutale, Martin Mwaura, and Humphrey Odwor. So today's webinar is going to be very brief for 2 hours on 5G network and planning. And we have a fantastic lineup of speakers that I've just mentioned. And I believe by the end of this session, you'll have learned a lot from the experts. They're going to be talking on different fields of their expertise, and they're very excited to share their knowledge and insights on 5G networks. So I would like now to hand over to our moderator of the day, Madam Catherine Kagwira, to take over as we now start the program. Welcome, Kathy.
Thank you, Anita. Good morning, good afternoon, and good evening to everyone. I know we are all gathered here from different parts of the world. As Anita said, we are grateful that you made time to be here with us for this webinar. It's a very timely webinar. I know we've all been, hearing about and reading about 5G around the globe, and for the Africans who are present, it's a revolution that's happening and that we should be adopting. But then what does this mean to us? What are the opportunities within 5G? So today as a Frailty, we feel it's a very timely time for us to have this discussion. And we're very grateful for the lineup of speakers that we have from their different expertise and experiences with 5G. So I do welcome you all on this webinar focusing on the revolutionary world of 5G networks. So as we gather here today, we embark on a journey to explore the cutting edge technology that is reshaping the connectivity as we know it. So throughout this webinar, we will delve into the key aspects of 5G networks, from its technical underpinnings to the diverse applications across industries, addressing challenges, opportunities, and future trends in the dynamic landscape of connectivity. So I invite all of us and encourage you to engage with our esteemed speakers, ask questions, and actively participate in our discussion. We are not just giving speeches or presentation, but we want to hear from you as well. And as we unravel the boundless opportunities that 5G networks bring to the table. Thank you for joining us today. And without much further ado, I will go on and invite our first speaker, Mr. Mwenya Mutale. The floor is yours. You can introduce yourself, tell us a little bit about what you do, and then get on to your presentation. Welcome, Mr. Mwenya.
Thank you very, very, very much for this opportunity to share my... Is somebody talking? Okay. Thank you very much for invitation to this webinar. My name's Mwenya Mutale. I'm the former Director General for Zambia ICT Authority. Before that, somebody speaking in the background?
Yeah, we'll just mute them and give us a second. Yeah.
Okay.
They are muted. You can go on.
Okay. Thank you very much once again. I prepared some presentation. It's not supposed to be very detailed, but I hope the participants will be able to understand the key concepts I'm going to share. like I was saying, I was introducing myself. My name's Mwenya Mutale. I'm the former Director General, Zambia ICT Authority, which is a Zambian ICT regulator for all ICTs. Before I became the DG, I was Director in charge of technology and engineering. And before that, I was also manager in charge of standards and type approval. I also held the position of Director Project and Strategy. And I was also a project manager for the implementation of Tier 3 data center in Zambia. So I'm coming from a technological background. I actively participated in the ITUT sector regarding especially study group 13. So I'm very much acquainted with these Gs, second 2G, 3G, 4G, 5G, and indeed 6G. So what I intend to do in this webinar is to share, number one, the key concept of standardization and the regulatory aspect of it. And at one point, I also want to share the 5G roadmap we put in place in Zambia so that we could adopt 5G and how we intended to actually regulate 5G. So without much ado, allow me to quickly browse through this presentation. Okay, I had to prepare this presentation when Jonathan actually asked me to do this. Some of the aspects of the presentation I did a long time ago. It was mainly focused with evolution of mobile technology. So I'm going to quickly go through the evolution, mentioning the key aspects of 5G, technical standardization and the objectives, focusing on the multiple access techniques and emphasizing the need for spectral efficiency, which the regulators are very, very much involved with, and of course, the user capabilities. And then I'm going to talk about standardization itself and the role of the standard development organizations, but focusing mainly on 3GPP, which I'm going to introduce and explain at length the process for standardization, so that we understand the meaning of the current state of affairs and where we're going to go from there on. So, mobile telecommunication is highly governed by standards to achieve economies of scale. The idea of standardization is actually to introduce interoperability, global interoperability, and economies of scales. The best example of a global standard was a 2G standard. When the second generation mobile communication came, actually there was various of them. We are going to see later on in the presentation, and we are going to see how the 2G became a global standard. In fact, it was arising from the 2G global standardization that the 3GPP project was born, and we had 3G, later on 4G, and later on 5G. So various standard development organizations, which I'm going to introduce, actually, they maintain those standards. And let me quickly go to the next slide. Of course, I was talking about interoperability. That's the main reason why we do standardization. And I'm sure Afrauti is running a course which is entitled The Role of Standardization and Interoperability. So that's a very, very important aspect of interoperability is standardization. And obviously, vendors and manufacturers are leading in standardization actually, together with the member countries, member states, under the ITU process. Let me quickly go right to the main standard development organizations. You must know that 3GPP is a lead organization, SDO, when it comes to 5G, 3G, 4G. We also have got IEEE playing a critical role in standardization, especially when it comes to Wi-Fi, Wi-Fi 6, ITUT obviously works closely with other SDOs. And then we've got ITUR, which is in charge of spectrum. As you are aware, spectrum is extremely very important in 5G. In fact, one of the key roles of regulators is to make available optimum spectrum for 5G so that the business model for 5G and the network deployment, they do not incur a lot of cost. So regulators and operators, and indeed in general, the industry must work together to realize the 5G adoption. Of course, there's another last SDO, which is very important, which has been extremely very important when it comes to the internet. This is called the Internet Engineering Task Force. Okay, the internet is a global infrastructure which is dependent on the open internet architecture, which IETF has been in charge of. So instead of going to each SDOs and going into details, for the purpose of this webinar, I intend to focus my efforts on the 3GPP process. The other processes for ITUT, IEEE, SA, IETF, I will not delve into this because it will take too long. So allow me now to just go to the 3GPP. Yeah. 3GPP actually was formed in 1998 with the aim of producing technical specifications and technical reports for 3G mobile system. That is the UMTS, Universal Mobile Telecommunication System. A UMTS is based on the GSM Global System for Mobile Communication Core Network and uses the Universal Terrestrial Access Ultra Air Interface. Okay, so the key thing here, the GSM was the first truly global mobile communication system. So building on the success on this GSMA, the 3GPP project was formed actually. The scope was later amended to include actually the maintenance and development of technical specifications and technical reports for GSM, including general packet radio service and EDGE, which is enhanced data rate for GSM evolution. The 3GPP also maintains LTE or long-term evolution or long-term evolution advance of 4G specification. So what I intend to demonstrate is the evolution of these three Gs, these Gs, 2G, 3G, 4G, and now 5G, and look at the future of 5G. Then I'll conclude by also giving a case study for Zambian 5G roadmap. Okay. So the next, okay, membership of the third generation partnership project, 3GPP, is the ARIB, ARTIS, TC, SA, ET. You can see there are so many TTA, TTC, known as organizational partners. Their aim actually is to determine general policy and produce reports and specifications that define the 3GPP technologies. So it's important for us to understand the standardization processes under the 3GPP so that we understand the meaning of a number of releases, which I'm going to talk about. Okay, 3GPP specifications are actually structured as releases, and standardization work is contribution driven, just like the ITU, by the way. So the specification actually are published up to 4 times a year following the quarterly plenary meetings. Companies or individual members do participate through their membership in 3GP organizational partner. Each release actually consists of multiple technical reports and specifications, each of which may have gone through many revisions. Often, a release provides new radio access technology and or advancements to an existing one. The first release, called Release 99, was completed in 2001 and specified the first universal mobile telecommunication system, UMTS, based on 3G radio technology, incorporating CDMA air interface. So the development of release is an ongoing process, and currently release 19 actually is undergoing progress, focusing on 5G. If I'm not mistaken, this release 19 has already occurred. Release 15 actually was a 5G release. I'm going to delve into that release later on in the presentation. Okay. Hello? Okay. Now, just to backtrack and talk about the main technical issues which all these Gs have been talking about. One key topic is multiple access techniques. Even 6G will be talking about multiple access techniques. So it's technical people, I don't know who are engineers in their networks, but the key thing about these generations is multiple access, the evolution of multiple access. If you can see from the table 1.1 there, okay? This was from Motaba report, Motaba and et al., which is a detailed report on multiple access techniques for 5G and beyond. I found this table to be very instructive. Okay. Of course, first 1G was talking about frequent division multiple access in terms of multiple access techniques. And then 2G went to TDMA, and the 3G actually was CDMA. Then 4G went actually to multi-carrier kind of modulation, which is orthogonal frequency multiple access, which actually 5G is also focusing on. Orthogonal frequency multiple access, it's a multi-carrier access. And if you look at the first G, it was just FDD, 2G and the first G, 1G is frequency division duplex in terms of multiplexing technology. But as we go high up to 3G, 4G, 5G, and 6G, there is flexibility in terms of duplexing methods. If you are good regulators in this webinar, note that the frequency arrangement you design for this 5G or 4G, you have to decide a combination or just a pure TDD or just FDD. But it appears TDD for me is spectrally efficient. It could be more complicated to implement. Of course, the key notable examples of these generational technologies, in first G, we're talking about analog mobile phone system, AMPS, NMT, and of course 2G. Like I mentioned, GSM was a truly global standard. 3G mainly use WCDMA, and of course, for 4G, we have got long-term evolution and LTE advanced. And then for 5G, we've got 5G new radio. So this table actually does give a summary of the multiple access technologies which have been used and which 5G is using. Here is just an explanation of multiple access technologies, starting with the FDMA, DMA, CDMA, and DOFDMA. So D is actually the multiple access technology of big interest because it actually has got huge capacity improvement. I must say, when I go back to this table on multiple access technique, we've been traditionally using OFDMA, but the new concept for 5G and 6G actually is what we call NOMA, which is a new technology for non-orthogonal multiple access, which is under research. For those of you who want to have academic excellence and get a PhD, you can immerse yourself in a NOMA and different platforms. So spectral efficiency has been at the heart of this mobile phone evolution. So as you can see, GSM and Edge, the spectral efficiency was very low, but we expect the 5G spectral efficiency to be very, very high, especially when you are using these advanced multiple access techniques. So this graph is just to demonstrate the key requirement for 5G. And of course, when people ask, what is 5G? 5G is about improving or addressing user needs, but most importantly, is to increase user capability. If you look at the first G in 1980, the capability is very low, but 5G, there's an exponential increase from 4G to 5G, almost 10 times. So that just demonstrates the driver of 5G. Yeah. Okay, this one, I don't want to go into some of the technical details of these multiple access schemes. But suffice it to say is that we need to focus on the OFDMA and NOMA, which are the key multiple access. And then here, as you can see, in terms of network architectures, we had a very simple architecture for first G, where we've got a mobile telecom office and the number of BTS and connected to the public switch telephone network. So it was simple. And then let me also quickly go to the 2G architecture. This one actually was using FTD, and it was also connected to the PSTN. But the key thing about this architecture, it was the core network, the way it was designed and became global. Most of the interfaces actually were standardized, apart from the interface between the base transceiver station and the base station controller, but all other interfaces. The user equipment, there were different manufacturers for mobile phones. So there were economies of scale. Many other subsystems were actually standardized, including parts of the core network. If you look at the gateway mobile switching center, the home location register, authentication centers, the saving GPR support nodes, all those things were standardized. So that became a true global standard. So upon this architecture, actually, that's where the 3GPP project was anchored upon, actually, to come up with the 3G standard. Okay, I won't go into details again into this slide. Let me just quickly go to the next slide. Okay, so these are the specific standards of 2G in terms of TDMA, the modulation schemes, the channel bandwidth, all those the time slots which were used. Okay, this were a detailed implementation. But also note that we also had the IS-54 standard, which was also a 2G standard, which is was also TDM based. It was also digital modulation and the channel bandwidth of 30 kilohertz. But again, we also had IS-95, which is CDM1. But again, it wasn't very popular. It was only GSM standard, which was very popular. So then this is the actual famous 3G standard, which was the first radio standard which the 3GPP project actually focused on. As you can see, the core network is quite similar to the 2G network, but the concept of node B was introduced. The radio network controller was also introduced, and there was an improvement actually in terms of node B was given more control, power control, modulation, and spreading, which was not an error correction, most importantly. So that was a big improvement from 2G. And of course, we're using CDMA in this technology. But quickly, because of user demands, this standard actually was replaced by the 4G. Okay, don't worry about the rate receiver. This is just one of the methods of improving network performance. So let me not go into the detail for the rate receiver. Okay. 4G network. 4G network is very interesting when it comes to 5G, because every 5G deployment, okay, to some extent depends on 4G network. You heard about standalone or non-standalone implementation, okay? So when they say non-standalone, it means that it depends on the Hello? Okay. So when you hear of a non-standalone or standalone 5G deployment, it's the reference to 4G network. Non-standalone, according to my understanding, is it depends on 4G network. By the way, by 2016, the USA had deployed 100% 4G network, and most developed countries actually had almost 100% deployed 4G. So when it came to 5G deployment, they were just building on the 4G network infrastructure architecture. So as compared to 4G, to 3G, the base station became known as Node B instead of Node B. Node B, and we had a core which was called Evolved Packet Core Network. And of course, the key thing which changed here, we began talking about control plane and data plane, and the entire core became, the entire network became IP, and there's what is called EUTRAN, Evolved UTRAN. So if you want to go into details, we can talk later on, but for the purpose of this webinar, I just wanted to focus on the architectural aspect and how we're going. By the way, if you look at the core network, the main elements are mobility management entity, HSS, which replaced the home location register and visitor location register. It's flatter here. We can see saving gateway and packet gateway and policy control, so rules function, which were new things like connection to the PDN, packet data network. As you can see here, connection to the PSTN is no longer there because PSTN is an older technology and you can connect 4G to various networks. Okay, so this became the multiple access network, the multi-carrier orthogonal frequency multiple access subframe. You can see there's 12 subcarriers. Obviously, this is a huge improvement to the 3G. Okay, we may go into the analysis of this multiple access substructure, but the key takeaway thing that this access thing increase the speed tremendously. Okay, allow me to, again, this is just an implementation of this 4G OFDM access, which I want to go into. Allow me, okay, the other thing which is important for this multiple access thing is a cyclic prefix overhead. So it's important that to avoid inter-symbol interference, this overhead must be added, and that's what in 4G network, this was solved. You may go into the details of that, but for now, I thought I should just highlight that one. Now, we talked about 3GPP release. Okay. So for 4G, we had a number of releases for 4G. Starting from release 10, for me, I regard like a serious 4G release 11. Okay. For each release, there was improvement. Okay. Whether it was carrier aggregation, as you can see, for each release, there are technical details for implementation of those releases. So as regulators, you must focus on the right standard. When an operator is claiming they've got 4G, for example, 4G can mean anything. Is it LTE? Is it LTE advanced? Which release are they implementing? As director in charge of technology and engineering, I was very specific about which 4G you are using. Because consumers, they take it for granted that 4G is 4G, but they may not understand what it means. Right? So you need to make sure that these operators, they've got the right releases. And again, how do you migrate a 4G network which has got release 11? Because a number of operators in developing countries, they may not upgrade their network as soon as possible. So when it comes to migration to 4G or to deploy non-standalone 5G network, it becomes a big problem, and interoperability issues can arise. So it's important to go to this 3GPP website and actually check the right releases and check with the network providers. So finally, this is the 5G architecture. Okay, as you can see, the control plane and data plane is flatter, and there's also G0B on the NG radio access network. The 5G core consists of user, there's what we call, that most of them are function. Police control function, there's a access management function, there's a, in fact, let me just go to the next one and explain what each one is. The key function which I find very interesting for purpose of cybersecurity is the access and mobility management function, which performs actually ciphering, integrity protection, mobility management, authentication, and authorization. The session management function actually performs user equipment, IP address allocation and management selection. We also have got unified data management, which performs subscription management, user data registration, and mobility management. The police control function in 4G, it was called PCRF, but now it's just called police control function, which performs police rules for CP function, etc. User plane function performs the external interconnect point to data networks and quality of service handling of user plane, etc. So application function interact with police framework for policy control rule. So these are the key components of the 5G network architecture. Okay. Okay. You heard about use cases of 5G. It's important to understand the use cases because these use cases actually were the drivers of 5G adoption. Okay, there are three main use cases. The first use case is called enhanced mobile broadband. The second use case is called ultra-reliable and low latency communication. The third and final use case is massive machine type communication. So can you imagine these use cases going to come to 6G, they'll be expanded. Instead of a triangle, we're going to have an hexagon. There'll be six use cases. Yeah. So if you look at enhanced mobile broadband, we're talking about 3D video, UHD screens, we can play in the cloud, AR, augmented reality. There's also industry automation. 5G also provide mission critical applications. Self-driving cars, you've heard about them in China already and US. They're self-driving cars. For us to implement self-driving cars in Africa, we need to have serious 5G deployment. The smart city use case is very famous actually. You need this utility system to connect to 5G. The water systems, the electricity system, and many other systems actually. And that leads to smart city. Smart home building, those are use cases. And allow me to just go to show you what ITSI has depicted pictorially in terms of use cases. As you can see, what I was talking about, self-driving cars, there's the work and play in the cloud, e-health, industry automation, voice calling, augmented reality. This is a view of European Telecom Standard Institute in terms of the 5G use cases. But there's also another interesting use case, which you must see from Tails. So this is how they depict the use case for 5G. Okay. Healthcare, smart cities. Okay, this one also includes, if I am not mistaken, satellite communication. The one good thing about 5G is what is called NT non-terrestrial components of 5G, or NTN, non-terrestrial networks. In other words, 5G and beyond will require integration between terrestrial communication and satellite or space communication. So that's when we're going to have a truly global network. Can you imagine this 5G is supposed to connect vehicular communication, vehicle to vehicle or vehicle to anything, remote surgery, also Internet of Things, environmental monitoring. I mentioned smart cities and remote medicine. Okay, digital wallets, connecting everything to everything. That's the true vision of 5G. Yeah. So going back to standards, the first 5G standard from 3GPP is contained in software release 15. Okay. What was it talking about? It was talking about the new rate, the 5G system, phase 1. The same release 15 was talking about massive type communication and Internet of Things. It was talking about vehicle to everything communication, V2X, phase 2. It was also talking about mission critical interworking with legacy system. Okay. We continue with the same release 15. Okay. Wireless LAN and unlicensed spectrum use. It was also talking about slicing, logical end-to-end network. I want to pause here. Network slicing is facing a lot of regulatory scrutiny, especially in jurisdiction where they talk about net neutrality. Why should do we discriminate traffic? There was a recent ruling in the FCC actually, where the FCC actually, they have argued that whatever they do with network slicing, they should not discriminate internet traffic. So that is a regulatory barrier to technological implementation. So I don't know what other regulators are going to do when it comes to network slicing. Okay. Another thing which this release talked about was API exposure, third-party access to 3G services. It was also talking about service-based architecture, SBA. And this specification actually was also talking about further LTE improvement, mobile communication system for railway. Obviously, as you can see, the first release 15 was assuming that the implementation of 5G was going to start with non-standalone 5G before it goes to standalone 5G. So that was the implication. Okay. So before I conclude this presentation, I think I've spoken quite a lot, but I must mention that it's important for us to understand the background, for us to start having meaningful engagements. So how does 5G compare to 4G? Okay, let me go to peak data rates. 4G is about 1 Gbps, okay, downlink, and half a Gbps uplink. But 5G, which in ITU circles is called IMT 2020 and beyond actually, is downlink 20 Gbps and the uplink 10 Gbps. As you can see, the improvement for peak data rates for 5G, 20 times downlink. And this is almost 20 times uplink as well. Okay. Area traffic capacity, Mbps per square meter. We've got 0.1 Mbps per square kilometer and per square meter, while 5G is about 10 Mbps per square meter. Okay, that's almost 100-fold increase. Network energy efficiency. Okay, 4G is 1, but 5G is going to be almost 100 times less consumption of power. Connectivity density in terms of things connected, devices connected. In 4G, we're talking about tens of thousands, but 5G, we're talking about millions. The latency in 4G is about 10 milliseconds. But this latency in African arrangement, I don't think has been achieved. Most of the latency in America is 30 milliseconds. But a true 4G network proper release, maybe it is 14, 13, you find that the latency is quite good. But 5G latency is supposed to be 1 millisecond. Mobility, 350 kilometers per hour, but 5G is going to handle highly mobile users. Spectral efficiency, which is a key important for regulators. 5G is going to be 3 times. And the user speed data rate, 10 times that of 4G. So this is how we see 5G performing, coming from 1G, 2G, 3G, 4G, using multiple access schemes. Now, allow me to quickly show you the 5G roadmap, which you can learn from Zambia. Okay. When I was the Director General at Victor, we actually did a 5G roadmap for the country. I'm sure you can see the presentation. So this presentation was made at the stakeholder workshop when we were launching the 5G roadmap. I thought we could learn 1 or 2 things from this. What we did a 5G consultation where we invited all the stakeholders to supply their input regarding availability of spectrum and the use cases. Okay. Hello? Okay. Hello?
Hello, we can hear you, Mr. Mwenya.
Somebody was speaking, so I thought.
No,
Okay.
they're muted, yeah.
Okay. Let me just see. Okay. You can see the representation?
Yes, we can see it.
Okay. Can you see it move? It's moving?
Yes, it is.
Yes, it's moving.
Okay. So
Yes.
Here at this stakeholder workshop, we actually talked about the use cases, the 5G spectrum public consultation, and the key spectrum issues we are facing as a regulator. And most importantly, the 5G roadmap, which we are putting across. The idea as regulator was to actually encourage regulatory sandboxing. We are encouraging the adoption of 5G because industry was slow to move. So in this particular situation, we wanted to encourage the industry actually to deploy 5G and deal with many other issues, especially quality of service, and offer consumers with very exciting possibilities. So this was a regulator-driven approach towards encouraging 5G deployment. So I've given, okay, like I said, we did a survey which identified inadequate frequency spectrum as one of the key challenges and risks to successful implementation and adoption of 5G technologies. So at that time, this is what we understood the use cases. I won't dwell on this because I explained the use cases in the other presentation. So the public consultation, okay? We actually consulted widely and we received 420 responses from 14 local and international stakeholders. So as you can see, most of the responses we had was from mobile network operators, 22%. We had the manufacturers who respond to 21%, broadcasters, 14%. We had industry association, 14%, and international satellite.
Living room.
And hello? And we had also international satellite operators, 22%. Okay. So then we identify the key bands, because spectrum is an important component for 5G deployment, especially for regulators, even most countries, 5G depends on spectrum. So the key spectrum bands are in the high bands, mid bands, and low bands. Okay, this was at 2020-21, but after WRC 2023, there are new bands which have been allocated to 5G. So we are 26 gigahertz band, which are used for high data capacity for traffic hotspot and for small coverage. This 26 gigahertz band is actually called millimeter wave. Okay, mid band from 2600 megahertz to 500 megahertz. Now, this frequency band has been expanded. We've got a new frequency band from 33 to 3400, 36 to 3800 megahertz, and in the 6 gigahertz band, there's been allocation. And also 4800 megahertz, there's a new band for 5G there. So the best compromise between coverage and capacity. And these bands actually, they're critical for the launch. And I must say, in Zambia, we allocated 3500 to one operator for experimentation. We gave them 100 megahertz countrywide so that they can experiment with the 5G deployment. And we gave them 6 months, after which we're going to license. So that is what we call regulatory sandboxing. Low band, diesel dividend. Okay? Actually, we had 700 megahertz and 800 megahertz, okay, which we auctioned actually. This was the first dividend we auctioned, and in that first auction, actually, we raised about 26 million US dollars. I'm not saying that we should be raising a lot of money from this. In fact, the cost of this spectrum was quite cheap compared to other developed countries. So actually, we did very well. Okay. Okay. What were the key issues? Okay. The key issue was supposed to allocate highest values, socioeconomic use, while protecting incumbent users. So we wanted to use market-based approach actually to allocate spectrum. Okay. And there was a requirement of contiguous 80 to 100 megahertz channel that was required. But that one may be a myth now. With the carrier aggregation and with huge chunks of 5G which have been allocated, regulators, I think, they can give each operator at least maybe 400, 500 megahertz of spectrum. So we had an issue. We were worried that the operator holding, which they had, did not adequately certify the minimum spectrum requirement for 5G. Okay. So as you can see, that graph was trying to analyze the TCO index and the cost per bit comparing to various spectrum allocation. But I think the long and short of it is that the larger the spectrum you offer the operator, the lower the cost. Okay. So we had issues to arrange the C-band so that the 5G deployment could be done. Okay. Recall the multiple access, the duplex, we're talking about TDD, FTD. So we had to rearrange some of these frequency band. We had to look at the IT recommendation, M.1036, and find the optimum frequency arrangement for those bands. So mainly we were using TDD actually for 5G. So this one was just analyzing various frequency arrangement and other services which were going to be affected. But some of these things would have been overtaken by what happened at WRC 23, especially between the 600 and the 700. There's more allocation for 5G there. Okay. So there were key issues. Remember, the duplex system, the 5G TDD system requires synchronization of transmission between adjacent operators assignment to prevent harmful interference. So what we did, we proposal to facilitate and encourage operator-led solutions through appointment of the working groups. These are the working groups we came up with, and this is the activity we came up with. And I must say, the regulator must work with the industry actually to solve a lot of these problems together. So, and then this was our 5G roadmap, okay? In terms of spectrum release, okay? Q1 2022, there was simultaneous release of 240 megahertz spectrum of mid and low bands, which is 800 megahertz, 2600 megahertz, and 3500 megahertz. And Q3, we wanted to start releasing some spectrum in 26 gigahertz millimeter wave band. 2023 release of 60 megahertz in 700 megahertz band. But this was brought forward because of operator demand. So the roadmap was changed midway, and instead this was issued in 2022. And 2024 finally, release of 100 megahertz in the band 34 to 100 to 600 megahertz. Of course, other bands, second wave of 5G spectrum release will commence beyond 2024. So this was done together with industry, and the way forward, here we were talking about the launching the 5G roadmap and talking about how we're going to offer the spectrum using competitive process. And most importantly, the minimum rollout obligation was going to be a mandatory requirement for the mid-band, high-band, large bandwidth assignment to ensure usage and provision of 5G services. So with that experience, I want to submit, and thank you very much.
Thank you, Mr. Menya, for your presentation. And thanks for shedding light on the essential aspects of 5G standards and regulations. And we appreciate that you've given a case study of Zambia with the regulator ZITA. At least you got the understanding the regulatory framework, how it's crucial in ensuring a harmonized deployment of 5G networks that prioritizes both innovation and security. Next, we will have our next speaker, Mr. Martin Mwaura, who will speak on the 5G technology. Mr. Martin, the floor is yours.
Thank you, Catherine. Can you hear me?
Yes, we can hear you.
So, my name is Martin, as Catherine has introduced me. I'm an engineer by training. I've worked in various organizations, both in telco and media. And currently, I'm an independent consultant on technology, ICTs, telecom, and broadcasting. And for a while, I've been also consulting for Fralti, mainly on telecommunications and broadcast technology. And I'm going to be looking at rather expounding on some of the aspects that Mwenya already discussed with a bias to technology. I must confess that I have not prepared a formal presentation, but I will share my notes so that we can just have an open discussion. Now, let me just turn off my camera so that I project my screen.
Martin, are you still with us?
Yes, Catherine,
Okay.
let me just share my screen. Can you see my screen?
Yes, we can.
Okay. Yeah, so I'll just go through my notes and talk over them. And a lot of the aspects have already been introduced by the previous speaker. But 5G is one of those very interesting and wide topics. But we always have to start from somewhere. So the first edition of the IMT 2020 specifications was published in February 2021, and IMT 2020 is the name that the IT uses for the 5th generation telecommunication standards. And since then, we've had more than 200 commercial deployments. This is all over the world, and there are at least over 1,000 commercially or publicly owned devices, while almost 900 of them are available. So to be specific, that 5G introduced a newer type of radio interface, which is more spectrally and energy efficient, and supports, a very wide flexibility in terms of spectrum utilization. That would be from the available UHF bands all the way to the millimeter wave bands. And this was first introduced in 3GPP release 15. And as it has been, when generation changes, then both the networks and the user side devices have to be compatible with the new standard. And what I would mention here is that maybe the core network is not very much of a headache as compared to the access network, because the access network has to deal with a lot of uncertainties and unknowns, manage mobility, devices that are not of the same, power class, for example. And so one of the biggest headaches in standardization for a cellular network would be to make an efficient and functional air interface. So, sorry, we already saw a couple of these from Mwenya's presentations, but this is just a spiderweb representation of his last slide before the roadmap he shared with us. But what I would not, because he already mentioned all this, all I would say is that even at the point of release 15, the actual technology was superseding almost all of these performance requirements as compared, as they were defined. So I would say that these were minimum, performance requirements. But one of the more important ones, like the peak data rate, is that field trials have already been able to exceed 140 gigabits per second. Of course, trials, but commercial deployment is another thing. But as we move on, this will be onboarded. The other thing is, of course, a variant of exactly the same pyramid that he shared. But what I would mention here again is that all these, the EMBB, the massive machine type communications, and the ultra reliable low latency communications are all evaluated against, these are 3 use scenarios which are evaluated against 4 geographical environments. For example, it could be in an indoor hotspot where the actual throughput that is required because of the population or the availability of devices requiring high throughput in the same area is high. The other one would be a dense urban, that is a normal urban area with a huge population. Then there would be a rural area where things like mobility would be of a greater importance than the actual throughput. And again, it could be in an urban macro where the balance between throughput and mobility is a requirement. And therefore, the previously mentioned performance characteristics are evaluated under the 3 scenarios of usage and under different geographical environments. Now, currently, the ITU has approved 4 IMT 2020, that is 5G standards. And the first one is the 3GPP 5G RIT, which stands for Radio Interface Technology, which in itself is a standalone architecture, which supports 5G turnkey deployments where you have a new radio core and a 5G core. And if you compare it to the previous generation of the 4G next generation core, it has reduced complexity. But of course, there was the need to support 5G new radio air interface on existing LTE core. So there is also the second standard as the 3GPP 5G SRIT, which is a set of radio interface technologies. And what is to mention here is that it incorporates both 5G new radio and release 17 of LTE upwards. Actually, I think it's from release 14. So everything from release 14 is contained in the part of 5G SRIT. That's why it's a set of radio interface technologies. Now, there is also the third one, which is the 5GI, which was provided by the Telecommunication Standards Development Society of India, which is an updated version of the 3GPP 5G RIT, but optimized for rural coverage. And this just shows that the considerations for use cases and scenarios in India may be different from Europe and, American requirements, and therefore the TSDSI decided to modify the 5G RIT from 3GPP to fit local circumstances. Now, the last of the 4 is the DECT 5G SRIT, and DECT, as we know it traditionally, is a digital enhanced codeless telephone. But this is not, the network architecture kind of follows the DECT from a layout point of view, but from a functional point of view, this is a pure 5G standard, which supports non-cellular applications. And in this case, then would allow autonomous network growth, decentralization, and so on. So it relies a lot on peering. So nodes can automatically discover their neighbors and therefore peer with their neighbors and try to look for the most optimal route to connect the internet, if I may say that, or to try and look for the most optimal route to connect to a service and application that they need to connect to. And so they can support wireless telephony, media streaming, IoT, smart cities, and so on. And they are aimed at enabling license-free wireless services where you do not require a huge network layout, providing cellular links, or having core network gateways and so on. So the 5G tech network will be mainly an autonomous mesh network where devices peer with each other and discover each other autonomously. Now, one of the key things that have made 5G possible is the fact that there has been a convergence of how we build telecommunication networks and also general computing technology. And at the beginning, if you look at the legacy networks that the previous speaker kind of laid out, networking was based on nodes, and there would have to be specialized network nodes. And there had to be specialized networking nodes that performed the functions that were required, either to route, control messages, admission control, all these things that would be, achieved by a network. And it meant that only that particular appliance or node would perform the required functions. But then starting somewhere in the early 2000s, we started defining networking by software, where you separate the actual networking from the device itself, such that you can have control, defined in software, and therefore you do not need that specific appliance. And then it started first by just separating those and having, let's say, a dedicated server that would perform the networking functions. But then we went into kindly, okay. So as I was saying that we, after, separating the hardware from, or the appliances from the networking functions, then there came virtualization, where you don't need dedicated machines, even if they are not. In the first case, if you can have a software-defined network, but then the software runs on dedicated computers or servers or infrastructure. But once we started virtualizing systems, then we do not need dedicated infrastructure to carry out the network functions. And a step further allowed us to, virtualize. Apart from virtualizing the system, the operating systems and so on, we virtualize the network functions themselves so that we can run them or deploy them from anywhere. And virtualization goes very closely, follows cloud and hyperscale computing, where compute resources, whether it's processing power, storage, routing and gateway and so on, is deployed at a very, very large scale, and any service could be implemented on all these hyperscale services from anywhere. And this is what has led to the explosion of the internet as we know it. And just because we were able to first define networking in software, then virtualize the network functions, then we could deploy them on the cloud. And we could go further and subdivide complex network functions into smaller services and microservices and deploy them when they're required or where they're required, using traditional internetworking techniques or software development and management techniques. For example, using APIs to get access to services and so on. And in the recent times, we are employing machine learning and AI. At the current moment, the scope of use of machine learning and artificial intelligence in 5G is mainly to manage the network, optimize the network performance. For example, looking at load balancing or energy efficiency or mobility management and so on. The network can use the available data to autonomously make some decisions, which in the classical networking sense would have required some sort of intervention by an operator or a configuration change. But right now, this part of machine learning and AI is being utilized to, improve network efficiency on all fronts autonomously. And even at the earliest point of publication, all 5G network functions are supposed to be cloud native. That means that they can be deployed from anywhere and run from anywhere. Now, just to mention how the core looks like. Now, the 5G core itself is based on full control and user plane separation, which is commonly referred to as CAPS, which was introduced in the LTE release 14. And of course, because it's efficient, it was carried over. And the 5G core also follows the service-based architecture, where in the service-based architecture, first you must implement network functions as virtualized functions. And a network function would be a very independent entity that has, constraints on what it can receive, that is the inputs, and also has a very defined set of outputs that it can give. And once you virtualize that, then in the service-based architecture, any of that function becomes an independent and reusable network function running from anywhere. And it would be, each function would either behave as a service producer or it could be a service consumer. And what happens in the SBA is that any network function will allow any other authorized network function to access its services. And therefore, there will be some kind of or a method to expose the functions capabilities through what you call the service-based interface. And the service-based interface uses a REST interface over HTTP. And as some of you may be aware, REST is one of those object access, I would say, techniques, not really a protocol, but mainly used by most APIs, either on the internet or normal software deployments. APIs will be deployed over following the REST technique, so that objects residing at different areas can be accessed. And therefore, in the service-based architecture for 5G, each function will, let me say, advertise what its functions are. And any other function that requires to use them, as long as it's authorized, can get access to those services. And so there will always be, a kind of bus interface system where the network functions are able to communicate with each other and, either give services to other functions or request for services from other functions. Now, the main network functions in a 5G core, will follow a bus and service interface, SBI interface, where each function will access the bus. And this is not 100% inclusive. I'm just giving an example of some of the main functions that will be required. If I could just hold on. So, for example, we have, as part of the 5G network, we have the capability to run network slices. And these network slices must have a function that, that is available so that every other user is able to know how many network slices are available within the slice that they're working on. And the user must be able to select the appropriate network slice, and therefore you have the network slice selection function. Then the network must be able to expose itself so that other entities that may or may not be part of the network are able to know what services the network offers. And there's also one of the more important functions, the network function repository, which is a function that can be accessed by any other function to find the capabilities of the entire network. And then we will have what when I was referring to PCRF, for example, in 4G, is a policy control function. There would be the unified data management for subscriber management. And of course, there's the application function, which is the way the network is able to allow other functions to run. So what has been defined is the reference points, and therefore this nomenclature with an F just shows the reference point for each function, which is the definition of the set of inputs and outputs that can be given to the function, or the outputs that it can provide. And if you were to go further with the network slices, for example, each network slice would have a slice-specific access function, which again has to be part of the repository for the network. There is the authentication part, there is the mobility management, there is also the session management functions. And because it's expected that a 5G core will connect to a 4G core, there is the interface to the MME, which is the mobility management element of 4G cores. And because we have a full separation of the control and user plane, it means that a mobile or user equipment will only access the control plane functions that it requires, but the flow of actual data only runs on the green line. That is the flow of actual data through the run to the user plane function and to other external networks, like any data network like the internet and so on, doesn't need to hit the control part of the network, because there is a full separation of the user plane and the control plane. Now, for the RAN itself, too sensitive, the 5G RAN is fully decomposed, which means that all the RAN functions have been spread across 3 different functional components. That is the radio unit, the distributed unit, and the central unit. And this is not new with 5G. Again, it has been there. There was limited part of it introduced in 3G, but the proper decomposition happened with LTE. But this, of course, will be governed by the air interface protocol demands. And without going into any details, there are different, the protocol stack on the control plane of a 5G network, of course, would start from the RF, which is the lowest level where radio transmission happens. Then there is a physical and there is a physical layer. Then there is a medium access control. Then there is radio link control and packet data convergence, and then the radio resource control. Now, these are protocol layers within the radio access network. Now, as you can imagine, there, even however much we utilize, general purpose computing techniques, the RF layer, that is the radio frequency layer, will never be done by anything else but a radio. So the radio unit will be the one that provides the actual radio transmissions, but all the other layers above it, that is physical MAC, RLC, PDCP, and RRC, can be split across the 2 other devices, that is the distributed unit and the central unit. And depending on how the network is laid out itself, some of these 3 units, while there are 3 logically independent units, can actually be part of a single physical unit. And therefore, this gives rise to very flexible modes of deployment of the 5G RAN. And on the other hand, the 5G RAN itself is fully disaggregated, which means that the RAN software does not depend on any specialized hardware. It's based on software definition, and it's possible to also virtualize the RAN software. Of course, there will be limitations because when we say, or rather not limitations, but rather considerations, because when you're going to split where any of these functions is happening, either on the radio unit, on the distributed unit, on the central unit. And remember, the central unit and the distributed unit could be, housed in a remote data center, on the cloud, they could be virtualized, and so on, many flexible configurations. But you have to take care of the protocol requirements, whether it's real-time or non-real-time. So because you want also to reduce on the latencies, the real-time functions must be very close to the users. For example, scheduling decisions and so on should be, as close as possible to the air interface, while other non-real-time functions could be located further away, which would not be sensitive to latency. And this, when you can virtualize the functions in the central unit and the distributed unit, then it's possible to run these functions and host them on general purpose commercial computing hardware. That is unlike the legacy systems where you would have required to have, very dedicated hardware. This all you need in this case, when you can virtualize and run them on the cloud, all you need is compute capacity rather than the device itself. In
Hello,
a lot of
Martin.
cases,
Sorry.
From our side.
I think we've lost Martin. Martin, are you there?
Kathy, I'm back.
Oh,
I don't know
okay.
what happened. Yeah. So let me share again. Where did you lose me? Can you hear me?
Yes, we can hear you.
Sorry for that. Where did you lose me? Here.
Yes.
Okay. Some of the techniques that the 5G technology uses is, first of all, using the orthogonal frequency division multiplex to guarantee multiple access. And as the previous speaker mentioned, we use CP, that is a cyclic prefix, to improve the reliability of the OFDM. And the OFDM is key because it allows better spectrum utilization. Because of orthogonality, means that carriers are able to overlap with each other without causing interference, because they are 90 degrees orthogonal from each other. And OFDM itself is also very robust, or performs quite better than the other, techniques in terms of withstanding multipath fading effects. And it's able to accommodate both time division duplexes and frequency division duplexes. And on top of that, we use very high efficiency modulation schemes, depending on scheduling requirements. 5G is able to use QPSK all the way to 1K modulation, that is 1024 QM. And this would depend on, channel state information it has received from devices. If the radio conditions are very good, then use higher modulation schemes. If messages are required to be transmitted with very high probability of successful delivery, then we use lower modulation schemes as low as QPSK, dependent on, the robustness required and the state of the channel. And therefore, we can be able to get close to the required target efficiency in bits per hertz. When you look at the entire combination of the different modulation schemes that are available. And the other technique that is very important to 5G is using MIMO antenna systems. And a MIMO antenna system is a system that employs more than one transmit antenna and also employs more than one receive antenna. There are different implementation of these MIMO antenna systems. They were introduced as early as 3G, but the real utilization for these at a massive scale is happening in 5G. And when you have more than one, in traditional networking, traditional radio communications, you would consider even a simple diversity scheme as a multiple antennas system, where you would probably have, a single transmit with multiple receivers, which was even experimented or used in 2G, but it was just referred to as a diversity receiver. But when you have the capability to have, parallel streams at the transmitter and at the receiver in both directions, then you have a true multiple in, multiple out. And you could have a 2x2, you could have a 4x4, you could have an 8x8, and so on, depending on the complexity of the transmit and receive device. And this allows a lot of possibilities. For example, the capability to perform space-time coding and spatial multiplexing, where you would say that a slightly differentiated version of the same signal is fed on two different antennas over the same frequency, for example. And convolutional and mathematical coding allows the separation of the two, even though they are using the same frequency. And it would mean that if you only have one frequency, and on this frequency, let's say you have a maximum transmit capacity of X bits per second. If you had a 2x2 MIMO with space-time coding, you can achieve 2X bits per second, because you will transmit two parallel transmissions at the same time, but they are coded differently in time. And because the antenna systems are not multiple, and therefore they are not located at the exact position, then you can be able to differentiate between the two parallel streams and either use them to achieve a higher channel throughput or use them to achieve robustness. In the case of robustness, then in antenna stream 1 is duplicated, the same signal is duplicated in antenna stream 2, and therefore you receive both and make sure that the signal is not received in error. If robustness is not the concern, but capacity is a concern, then you can spread the user data across the two and you achieve double the maximum data rate. Now, these MIMO antenna systems will also allow beamforming and beam steering. And it's because at the heart of any MIMO system, there is a phase shifter that allows differentiation in phase. And if you remember the basics of radio transmissions or basic wave theory, you can either be able to combine two waves or rather two incident waves that arrive at a specific location together. Depending on the phase differences between the first and the second one, you can either have constructive interference or destructive interference, where in the case of constructive, the signals are received additively, and in the case of destructive, the signals cancel each other. And therefore, you can, with now the coding, you can be able to target a very specific area by altering the phases and the coding of transmissions coming from different antennas. And therefore, you can be able to have a very good signal to noise ratio at an area where that would not be possible if you didn't have multiple antenna systems that are separated in space and phase at the same time. And if that is possible, it means that if you continuously alter the phase of the signals, then you can force the perceived coverage beam to move depending on where you want coverage to be. So apart from improving the signal to noise ratio, you are also able to specifically define where you want coverage and deliver coverage at that place, as long as the transmission from the multiple antenna systems is received as intended. The other technique used by 5G RAN is carrier aggregation. And carrier aggregation, remember, we earlier said that 5G is able to use all available spectrum, all the way from UHF band to the millimeter wave. But there is also the aspect of what we call the component carriers, which there is need for flexibility because of differences across different countries in how spectrum is assigned, even the fact of the availability of the spectrum. And for example, at frequencies below 1 gigahertz, spectrum is very scarce in the UHF band, and we don't expect to be able to get access to spectrum that's contiguous, wider than 20 megahertz. However, to get to delivering 20 gigabits per second, even at the current state of the technology, you would need carriers that are way wider than 20 megahertz. So 5G allows component carrier aggregation, and the aggregated carriers don't have to be in the same band. They could be in different bands, and they don't have to be the same size. They could be different sizes. Knowing that 5G will support very narrow band carriers, from, let's say, 200 kilohertz all the way to 400 megahertz. And the very narrow band carriers at 200 kilohertz provided to make sure that low power applications are possible, because we get better sensitivity of devices at narrower carriers, while the very wide carriers at 400 megahertz are supposed to provide extreme throughput. And we can aggregate theoretically up to 16 carriers, each of up to 400 megahertz width. But the current state of technology that is available, I think in either FDD and TDD, we have about 6 component carrier aggregations on the downlink, and 2 component carrier aggregation on the uplink, of course, because the capacity or the capability of the user equipment is way less than that of the Node B. So the Node B can aggregate up to 6 component carriers at the current state of technology. But from a specification point of view, we should be able to aggregate up to 16 carriers, giving us an entire 6400 megahertz usable cell bandwidth. And of course, depending on the use case, this would be demanded at very extreme urban hotspot kind of use. Now, the other technique is the intercell interference coordination, or ICIC, where cells are able to coordinate interference among themselves. And one of the characteristics of OFDM is that subcarriers are, generated using a mathematical scheme. And so by altering the mathematical scheme, you can change how the OFDM subcarriers are allocated, and imagining that most 5G networks will have the same frequency, will use the same frequency across an entire area, then it would be prudent to be able to schedule different power levels at the edge of the cells. And because the subcarriers are generated locally, then if you coordinate with neighboring cells, then it is possible for the entire network to generate on the fly subcarriers that do not interfere with each other. So for example, dominant carriers that extend to the edge of the cell in cell A, which is neighboring cell B, will only be used towards the center of the neighboring cell and so on. And in this way, we are able to mitigate the effect of interference, because it can be quite, interference can be quite an expensive thing in terms of how much throughput we achieve if the network doesn't have any method for managing interference. Now, the 5G RAN is also able to use all available spectrum. And in the current release, this includes dynamic spectrum sharing between 5G and 4G. And this is to, for example, allow seamless migration, because there may be networks that were deployed before 5G that are LTE advanced networks. And if there is a need to use the same frequency for 5G or to offload traffic into the 5G cell, then the same frequency that has been allocated to the 4G cell can be allocated to the 5G cell, but the 5G cell will only use it dynamically, and therefore it may be able to accommodate 4G only devices over the 5G network, and that would allow, for example, switching off or easing off traffic from 4G to allow seamless migration into 5G. Now, all these techniques are used in concert, and so we end up with a very dynamic or a mixed RAN topology, where you could have within the same area a classic RAN where all the three components of the RAN that we saw are, in the same physical location with the radio unit, because the radio unit is the final part that provides access to user equipment. And in a classic RAN, then you'll have the distributed unit and the central unit there, although it does not negate all that we were saying, that the DU and the CU functions are not dependent on any specialized hardware. And then you could either have your RAN distributed or centralized, and the differences between that would be, if the distributed unit, and this is a logical function, is located with the radio unit, then your RAN is distributed. But if it's located away from the radio unit, irrespective of the topology, then your RAN is centralized. And the centralized or distributed RAN could be running from the cloud with virtualized services. But even the classic RAN itself could be virtualized on standard computing hardware, at the node B location. And this allows a lot of flexibility in deployment, depending on the use cases. If the concern is high mobility, then you can decide where to place RAN nodes for best mobility. Or if it's in dense urban area where the more important thing is to have very high throughput, or it could be just connecting smart devices that do not really require a lot of throughput, but require a lot of reliability and so on. Now, if we were to look at the specific use cases for 5G technology, Mr. Mwenye before me looked at the regulatory aspect of it, but I would mention the specific use cases from a what is possible point of view. And to begin with, the first way that the normal consumer on the street interacts with 5G technology is through broadband access, whether it's on their mobile devices or on a fixed wireless access device, because depending on how the network has been deployed, 5G is able to give comparable services, to what has been previously only possible through cable fiber networks. Therefore, it means that broadband can be available for all, even from the fixed sense of it. From the mobile broadband itself, most of the consumers are already using it, but there have been areas for fixed wireless where deploying fiber infrastructure would cost a lot of money, or maybe not possible because of the terrain and so on. But with fixed wireless access, we can provide similar services, broadband services over 5G network. The other use case, and a lot of the time I'm conflicted whether multi-access edge computing is a use case or it's a part of the network, but there is an attempt to locate services closer to the consumers in order to reduce the routing cost, number one, and also to on one side, on the network side, and on the consumer side, to improve network performance of the services they're running. So there is the possibility to locate applications as close as possible to the consumer that is at the edge of the network, so that they do not have to traverse the core network, and after the core network, they go to some centralized cloud, either on the internet or on a national data center, which introduces latencies and so on. And so MEC itself is an evolution, and because 5G allows network discovery, then it is possible to locate third-party applications somewhere inside the network. For sure, it is inside the network because MEC is located between the core and the radio access network. And maybe this is just a feature that 5G accommodates to allow better customer experiences on applications. The other use case for 5G technology is network slicing itself and having different verticals. But I would look at network slicing as the capability to have seemingly autonomous networks running over the same physical infrastructure. So it doesn't mean that, it wouldn't mean that there is treatment of different traffic different treatment of different types of traffic. But what network slicing would open up to is for example, being able to offer the network as a service where an infrastructure operator just deploys infrastructure but doesn't really offer the actual services to consumers, but provides segmented parts of that network to different users who may have very, very different user requirements, for example, in terms of latency, in terms of throughput, in terms of security, and so on. And all these different network slices would support different verticals, because some other use cases have different demands in terms of reliability and so on. So it's possible to have the same physical network that carries out, that operates as very different logical networks, and it's only available to those that have subscribed to the different slices that they want to use. And because of the fact that the resources should be used as efficiently as possible, there's probably no need to dedicate resources all the time to a service that doesn't really need them. Those resources can be available for a slice when another part of the network is not using those resources. 5G can also be used to make private networks where the network doesn't really have to be a cellular operation, but using 5G bands and 5G technologies, you can, kind of replace, for example, operations technology for different sectors like energy, mining, and so on. So instead of them, relying on a publicly available network, they have a private network that only works, for example, to interconnect their systems. And a lot of the time I see it, the best use case for private networks is to replace what we have come a lot of the time to depend on Wi-Fi, especially for larger enterprises, for campus-like installations, institutions, hospitals, and so on. Because Wi-Fi is unlicensed, you cannot control the contention and so on. So if the spectrum is available, and I believe that as more and more exploitation of the higher bands, mid-band and millimeter wave becomes available as 5G evolves, then we may be able to replace a lot of the services at the local level that really require, security. We offload them from Wi-Fi and put them on local private networks. And because at the higher frequencies, the reuse patterns can be quite dense, and therefore the possibility of interference is lower at the higher frequencies and so on. And there's also the aspect of using 5G for IoT, and it's not a new thing. We have had sensor networks being connected over low power ones for a very long time. The problem is that most of them have been very proprietary, and the need to deploy a network kind of reduces the reach. And if we can extend these using existing 5G cellular provisions for IoTs, and if you look at the protocol, there is a lot of effort that is made to accommodate what was achieved by low power ones and standardize it into the 5G technology. For example, having narrowband devices and reduced capacity devices and so on. This as also part of the IoT, the general umbrella of IoT. We have, for example, the intelligent transport systems and the cellular vehicle-to-X. The ITS and vehicle-to-X have existed before using different spectrum bands, mainly have been proprietary, but 5G and vehicle-to-X are coming together to standardize cellular vehicle-to-X and intelligence transport systems so that we extend the capabilities from a throughput point of view and also a reach. And of course, most ITS systems will require we'll have some form of applications that run on a network somewhere, and the cellular side of it connects the V2X infrastructure that could be on the road, on pedestrians, on vehicles, and so on, to access the application parts that are running on some core network somewhere. There's also the need, or rather the specific application on industrial automation, where for the purposes of the very time-sensitive networking, large industrial automation has had to deploy very specific networks. And in the case of the time-sensitive networking is that in as far as we want to have very low latencies, in some applications, the jitter on the latencies themselves may be an issue. And in previous cellular networks, it may not have been possible to define QoS profiles that are very specific to very specific applications, and it may not have been possible to guarantee that there will be no jitter on latencies and so on. And therefore, 5G will allow this kind of networks to integrate even over a wide area with already existing industrial automation systems. And I'm talking about the very critical ones like autonomous vehicle control and so on. There's also the aspect of extended reality, which is an umbrella for all the types of either virtual reality, augmented reality, or mixed reality, cloud-based gaming, and so on. And up to now, there has been a very big limitation on how much mobility that XR devices can have, because on one hand, you need a lot of processing power. And if I would give the example of having a head-mounted display, then with all the processing power that is required, the HMD would either heat up or be very poor on energy, and therefore battery lasts a very short time. So then you find that the real, yes, Kathy?
Hi.
Am I over my time?
Yeah, we're over, because we need to allow a Q&A session and also a word from the next speaker.
Okay, I have 2 slides then. So anyway, 5G, because of the low latencies that are required, will allow us to offload some part of the processing for VR, AR, and so on onto the network side. And because of their nature, there is an interaction between the real world and the virtual world. Latencies is a big deal, and reliability is a big deal. But if we can offload part of the processing to the network side and be able to deliver it with very low latency and reliably to the mobile part of the XR devices, then this is a good use case. And you can think of anything controlling, again, autonomous vehicles e-medicine, teleshopping, and so on. And one of the final is 5G SFN digital broadcasting, which is directly analogous to digital video broadcasting as we know it today, only that with just a couple of tweaks on scheduling and so on, you can be able to simulate a high power 5G SFN delivered directly to mobile devices, because today mobile devices cannot receive a digital broadcast because they do not have the same receiver chipsets. But you can be over 5G, you can deliver broadcasts directly to mobile devices and follow the same topology, having high power, high tower transmissions that could be as far as 100 kilometers away with very, very high mobility. And this has been tested in venues across most of Europe. And I think most recently, Super Bowl tested how to do this. And because we have been already receiving multimedia services on our mobile devices, the fact is that traditionally they're delivered in a unicast manner, which doesn't scale very well because every new user requires the same capacity. But if you can replace that with broadcasting, with an SFN broadcast, then you are able to use the resources very, very efficiently. Now, where we are today is 5G itself is already mature, but it's evolving. Starting from release 15, there's where the main deployments were just EMBB, the 3 points of the triangles as we saw them. Then in release 16, we have unlicensed relaying. For example, in a CV2X operation, you can have a device relay to another device that is outside the coverage area. And this is now became 5G evolved. And in release 17, also 5G evolved. We have reduced capability devices. These are devices that perform very well with very, very low complexity receivers. And then we started introducing non-terrestrial networks and broadcasting and the use of millimeter wave bands. And in release 18, also 5G advanced, we have been able to incorporate AI and machine learning for automation. And now with currently, the release 19 studies are ongoing and development is ongoing. Again, focuses a lot on network efficiency and also having massive and distributed MIMO. And there's also a better way of managing mobility, for example, triggering it at layer 1 or 2 so that the network is more responsive to mobility requests. And we expect that, as there will be newer releases like 20 and 21, but by then, somewhere around 2028, 29, the specifications for 6G will be complete because the studies and the requirements have already been, the requirements have been put forward and the studies are ongoing. So I would like to look at the current state of technology now as 5G advanced and others referred to beyond 5G and so on. And the same usage scenarios will evolve into the future and incorporating the 3 usage scenarios that we have seen. Soon, then we'll have, even way before IMT 2030 or 6G standardized, Then we want to extend EMBB to UMBB, have high mobility broadband and high stability broadband. Then we improve the performance of the critical communication. So from MMTC to ultra supercritical communications. Then at the massive machine type communications, we have ubiquitous massive machine type communications available everywhere. But for IMT 2030, that the three expanded scenarios actually become a hexagon, where you have three other scenarios where you have broadband for all with all earth coverage, and of course with the availability of high capacity and low orbit satellite systems, which will be, right now the non-terrestrial networks are still not fully integrated to the 5G, but some 5G devices are coming with chipsets that are able to connect to the non-terrestrial networks. But if we have 5G or new radio for NTN, which should happen somewhere, in about 1 or 2 years, then we'll be able to achieve broadband for all earth coverage. And then we integrate compute AI services into the network. Right now, I'd mentioned we are using AI for network optimization and so on, not really as a compute service for users. But we, in the expanded scenario, will have compute AI services available as part of the network. And then there is one of the more interesting parts, the sensing and communication part, where we use the network as a sensor. And it's looking at it as same way we look at radar. And therefore, your network can be able, with the incorporation of the compute AI and so on, and the availability of processing capabilities, then the network itself can act as a sensor. So it can actually build a 3D image of its surroundings. In other terms, what they call creating digital twins of the real world. Because today, our location-based services, for example, only use the network for localization. Then you have to have very many other sensors to manage the environment around the device that is being localized. But when you have sensing and communications over the same network, the network can build a 3D model of its surroundings, and therefore make location-based services way more accurate. And of course, there will be a trade-off between how much network resources are used, or rather RF resources are used for sensing and how much are used for communication. But it doesn't really matter, because every time you communicate or another device communicates, signals will bounce off all available surfaces. And if the network can sense them, then it can be able to build a 3D image of its surroundings. And that is beyond 5G. And the last slide for me. Sorry, Kathy, I went over my time, and thank you for listening to me.
Thank you, Martin. Definitely, you are is it a lecturer or a facilitator? I am seeing lots of chats from the chat section of questions. To the delegates present, kindly allow us to have the next speaker. Humphrey, I'm so sorry. Martin and the previous speaker, Yale, they do owe you time. So you must see them behind the scenes to make up for that. But if you could take the short time possible, so that you can also allow the participants the Q&A section and allow also, if we have our head of training who has joined us, he'd like to give his remarks as well.
Yeah, sure. Thank you, Catherine.
Okay.
I hope I'm audible.
Yes, you are audible.
Right. So thank you to the speakers who have spoken before me, and it was interesting actually listening to them. So I'm supposed to have a discussion on probably network planning mostly, that is in 5G networks. So to make it at least shorter, I'll just go over the key issues in network planning, but then again, understand that these slides will be shared with the delegates who are in the webinar, so that should be sufficient enough if any of us wants to get a bit more info. So I'll just share my screen quickly, then start. Hope, just confirm if you can see my PowerPoint slides.
Yes, we can.
All right, great, thanks. Yes, so the webinar, just building up from what the previous speakers have spoken about, that is the 5G networks, from the standards down to the technology itself. Now, if you focus on planning and product design consideration, that is where things get a bit more interesting. So I'll just give a bit background of myself, what I do. So I'm a telecom professional and technology professional mostly. I'm currently involved in research as a PhD researcher at the University of Cape Town, but also I am an academic as well, with some background with the Strathmore University in Kenya, where I offer services as a lecturer as well. But currently I'm based in Cape Town as a researcher working on 5G projects as my PhD research. So previously I've worked on computer systems, computer networks, telecom networks as well. But currently most of our work is on trying to build wireless testbeds, so around 5G and beyond 5G. And we are mostly focusing this on unique use cases. So you're looking at how can we support uncommon use cases in 5G networks. So these uncommon use cases for us at the moment in our lab is we're trying to support healthcare services on 5G. And beyond that, we're also trying to look at how can we get this working by providing an intersection of machine learning and AI into this particular network. So we're looking at ways to make the network more efficient in terms of supporting these unique use cases. That is the healthcare space. So that is a nutshell about me. So you can begin. So in network planning, of course, we have to introduce the concept of planning. So the essence here is we want to understand, like, how do we think of planning a 5G network, because we have understood that from the perspective of 5G, we are coming from a backdrop of change in technology, mostly from the 3G network, with a huge leap into an all IP network in 4G, and then with more efficiency being introduced in the 5G new radio in 5G. So we want to understand then, if that is the case, then how do we go about planning this kind of networks? So we'll first of all look at introduce the network planning aspects, then look at the steps involved in network planning. Then, of course, with network planning, there are a few things that are very important, mostly because with mobile networks, we want to tackle two things. One, we want to be able to offer coverage. That means we want our network to actually the reception at the edge of the network, of the edge of the cell, to be at least good enough for the user in a particular area. And again, we want, with that kind of reception, again, do we have enough capacity to offer to give the user some fairly good quality of service in that particular area? And then, of course, that most is driven by a number of cases, as we shall see. And that, of course, drives what we talk about in network planning. So in regards to network planning, mostly, the steps may be similar in previous generations, that is in 4G and 3G. But then in this case, if you're trying to look at 5G, we try and get the difference mostly that comes in network planning in 5G. What are the key considerations that we can have whenever we're talking about network planning in 5G? But if you've done some work on network planning as well, you'll find that most of the steps are actually somehow similar, borrow a bit of the concepts here and there in network planning in 4G and 3G as well. So again, we look at 5G site selection criteria, which again is mostly, we try and bring the context mostly to 5G, and then we shall look at the planning challenges we have with network planning in 5G. So Again, I'll just go over this very quickly. So planning, of course, means we have to determine the number of locations. So just switch off my video in case so I can save on bandwidth on some areas. So in terms of 5G planning, you're talking about, we want to determine, first of all, are we able to use the network resources available, both physical and virtual resources, in the most effective way possible. And at the same time, this is driven mostly by the demand from the users. So we're trying to create a balance here, right? So we have operators on one side who want to deploy low-cost networks. And then, of course, on the other side, we have to also deal with issues of capacity and coverage. And then, of course, quality of service as well. So if you look at planning from a particular perspective, it's mostly a balance. We're trying to see operators have their own incentives where they want to deploy, if I can call them in quotes, cheap networks. But at the same time, they want to also, they have contracts that they have to adhere to, and of course, standards and the regulations they have to adhere to in regards to offering some allowable quality of service, meeting some capacity demands and coverage demands as well. But at the same time, they also want to use the latest technology and then it deployed in the most efficient manner. So in the long run, with planning works, you're talking about, are we able to determine, maybe if you're talking about qualitative terms, are we able to determine maybe the number of base stations that you can have in a particular location? That is, in essence, in a particular area of coverage. What is the location of this base station? Where can we put them? And then, of course, the configuration of this base station in the deployment area. So in this case, again, we're talking about how then do we commission the base stations in a particular area so that we can be able to say you're offering effective or efficient 5G coverage and capacity in a particular area. That is the introduction of this case. But then again, I've highlighted the use cases here because, again, 5G is mostly driven by use cases, as opposed to the work that we've previously seen in 4G networks, where one network built to fit for all services doesn't really cut it anymore, because if you ask, because in one of the questions we normally ask whenever we try and explain our project, our current research project to everyone else, is the question that why 5G? What can't Wi-Fi do? What can't 4G do? And of course, the answer is with 5G, then we're talking about supporting use cases that are normally not able to support in normal mobile networks, because 5G in its sense has a number of technological differences that we normally don't see in 4G, one. And then, of course, with the ability for us to control the network and how it operates, that gives the 5G an edge. So 5G, if you look at it from a particular perspective, it has been built mostly for use case and common use case support and common use case support and demand, of course. So if you're looking at this, Martin has talked about use cases to do with massive IoT, vehicle to anything communication. And of course, those are the common ones that have been categorized in terms of the TGP standards. But if you go further, you can even look at uncommon use cases, which I think are very, very specific to the users of a particular case. So in our case, you're talking about healthcare. How can 5G support healthcare services? That is why, it becomes interesting now if you're talking about planning 5G network. So we have to also come back and look at what use cases do you want to support, which becomes very, very important. So moving on, after bringing that into perspective, then of course we've talked about the objective of 5G radio planning. You're talking about capacity. You're talking about economy of scale that we have to also consider. We're also talking about how many sites can we deploy to satisfy coverage, quality, and capacity. And then, of course, on the other hand, we also restricted mostly in 5G by these KPIs that are normally put out by the standard organization bodies. So we're talking about 99% availability, 99.9% reliability, and then of course we're talking about high bit rates. So again, if you look at this, then we are at a crossroads, because we're talking about cost, coverage, and capacity, but then we also have to meet some KPIs for us to say we're offering really good 5G connectivity. So shall we see, all these are balances that we have to consider whenever we're talking about 5G network planning. So in that case, then we then have to look at a few things. We're talking about network planning then. So of course, since it's a wireless network, you have to look at propagation of these wireless signals. So you have to consider things like configuration management, interference management, placement of the antennas. And then of course, we have to also look at the site itself. So you have to consider a few things when trying to select a site. So is there, in terms of, first of all, interference is one thing that you have to consider in that particular case. And also you have to consider, are there existing sites that are already deployed in that particular region? For example, I can give you a case. If you want to if you want to upgrade a network from 4G to 5G in a particular area, let's say an urban area, what are the potentials for us to reuse a few sites that are already available? Again, what is the potential for us to use the same frequency that was allocated for 4G? We reuse concept spectrum refarming. We refarm that spectrum and then use it for 5G. So I mean, all these are just ways for the operators in this case to actually find the most effective way of deploying 5G. So in terms of site selection, becomes interesting for us to find out, are there efficient ways for us to select a site based on multiple considerations here: capacity, existing infrastructure, and then of course frequency as well that is available. But more importantly now is backward planning and optimizing, because as we've seen in the previous slide, we have mentioned that 5G now talks about speeds, network speeds. Can even call them downlink and uplink speeds that are targeting more than 100 megabits, close to the gigabits per second. So that means then we can achieve new radio as a technology on the radio access network, as we've seen in the previous slides. So we have the radio access network, which of course gives us the AI interface for us to connect the different user user equipment, that is a mobile phone. In that particular case, we have new radio that has been designed with the different terminologies and the different ways it uses the spectrum for it to be able to give us some good transmission rates. So if you combine higher bandwidth availability in terms of the different terminologies on the radio access network, and then you combine that with effective schemes like using TDD on the radio access network, that of course on the radio access network, yes, you can achieve some high speeds. But then again, now we also have to consider backhaul planning, because we can have good speeds at the radio access network, but then the backhaul becomes a problem, because looking at the G node B as it is, if you don't have a good backhaul from the G node B straight to the UPF, that is the N3 interface from the G node B to the UPF, if you don't have sufficient backhaul for that particular kind of transmission, then we are in trouble. Because if you're talking about a user being able to get like 200 Mbps on their device, but then our backhaul network in this side on this other end cannot support that kind of traffic. If we have, let's say, 1,000 users, then you have a problem. Of course, the bottleneck is introduced there. Again, this backhaul again is translated again from the N3 interface from the G node B to the UPF, and then beyond the UPF to the data network, the N6 interface. Again, we must have some good backhaul capabilities there. So the puzzle in this particular planning purpose and backhaul considerations, we have to make sure if you're promising this kind of capacity, are we able to get it, first of all, from the data network? Are we able to get it from our backhaul? And also in cases where we're talking about now even more advanced networks like open RAN networks, where we have distributed the different functions of the RAN, where we have the control unit and the distributed unit in different locations. There we also have a frontal interface, which we also have to consider in terms of capacity planning, because if that separation in the open RAN of the CU and the DUs, the control unit and the distributed units in this case, doesn't have enough capacity in that particular case, then again we're in trouble. So backhaul planning as well is something you have to consider in terms of 5G and network planning. So again, it's important. Again, these are the tasks that we must actually look at keenly whenever you're talking about network planning in 5G. So beyond that, again, with 5G, I've tried to talk about a few things here. There are certain things that are unique to 5G. Of course, we are considering enabling technologies like millimeter wave. If you're considering millimeter wave, it becomes different compared to 4G, because this is a very high frequency bands for transmission. So again, if you're talking about millimeter wave, you're talking about very, very dense deployed networks. So we have base stations that are very, very close to each other for us to be able, of course, to offer connectivity at this communication speeds. But then again, if you're talking about this kind of millimeter wave deployment, currently they are I don't think there is any commercial millimeter wave deployment of 5G. But of course, with certain trials, you can see that this kind of deployment doesn't really suit outdoor deployment, so we want to penetrate these signals inside the building. So if you're inside a building, you can talk about deploying millimeter wave, and then of course will open up different use cases for us in that particular regard. So that's why I was talking about 5G being mostly driven by use cases, because the technology as it is offers us a lot in the toolbox for us to use. Then of course we've talked about massive MIMO again, where we have multiple antennas communicating at the same time, multiple antenna arrays communicating at the same time. So depending again with the capacity you want to achieve, you can use technologies like massive MIMO. And then of course, this again drives up a few things in regards to what you can do in terms of the cost that you can consider talking about this kind of technology and applying them in your planning, network planning and design phase. Then of course, you can talk about applying other technologies within the antennas, like doing 3D beamforming, effectively pointing beams to a particular user, and then adjusting that beam to different users depending on different parameters of the network. So all these are things that you can actually consider whenever you're talking about deploying a 5G network. And of course, I've talked about the 5G frame structure and the numerology, which gives a bit more in terms of how much bandwidth and some carrier spacing can we use whenever deploying a 5G network. So all these are things that you can consider technology-wise whenever you're talking about deploying and planning 5G network. So let's go quickly again over this diagram, a summary here. So we have the control nodes we want to cover in a particular area. Again, of course, you have the different deployment options, dense, very dense, ultra dense. All this can be supported by 5G because the FR1 frequency band, FR2 frequency band on the spectrum allow us to go from dense to ultra dense to very dense deployments. And then, of course, in this case, then we are also talking about the aim is optimum run dimension and planning. But then again, you have to consider all these inputs. So we have deployment options, which are we going to? Are we going for? We are considering mostly covering capacity and coverage. And then, of course, the output in this case is the 5G deployment and evolutionary option. Now, this is the output. These are the inputs that go into optimum run and planning. These are the output that we design in this particular case. And then again, I still insist, the desired deployment option mostly. And I think at this point, it will be important for us, even as we look at the deployment of 5G, to think of 5G in a particular case where we are moving beyond the MNO deployments of networks, mobile networks, to actually private deployments of mobile networks. So at least to give us the different options that are available to us. So the MNOs, of course, they have their own commercial interests in terms of coverage a particular country or region. But then, of course, if you now bring it down to local deployments to suit specific use cases like deploying in a particular factory to do some to help in production, to deploy maybe in a particular industrial port to help in planning container shipping and container movement a particular port. Again, those are different desired options that we have in 5G deployment. So all these are the different things that you must consider in that regard. So moving on, I'll try to move a bit quickly. Then again, of course, if you're talking about radio network planning, there are a few steps that, of course, you must go into. First of all, of course, the incentives, business planning, the business needs of the organization. And then again, you have to look at what spectrum is available, what capacity do you need, and then, of course, do a bit more of coverage planning. So we'll go into these details in a high level. We're skimming over the details. But then, of course, there are other advanced courses, I think, offered by Frailty that now go into details of this particular information in a bit more detail. So, so if you're talking about business planning, you have to analyze the needs of the business. You talk about the frequency, what is available for us to use. Is it free? Is it licensed? Is it licensed? Is it shared? Like, can we do stuff like dynamic spectrum access on this particular frequency or not? So these are the things you have to think about when you're talking about frequency planning. How do we access the frequency? Do you have to pay something? Is it free for use? Can we share it with someone else? How do we share it? What are the modes of sharing a particular frequency? And so on. So that, of course, will give you some output here, like the radio network information table. So this will tell you like the spectrum. This is what you need in terms of bandwidth. What aggregation options do you have to meet that bandwidth, capacity, demand? So these values here are just arbitrary for illustration. But of course, they are just what I'm illustrating what you can achieve whenever you're talking about the aim of this step here. So beyond that, I've talked about information gathering, because at the end of the day, mostly in terms of infrastructure planning, you want to find out like how many GNODBs do we need to meet capacity and coverage demand. So this is still naive from the point of view where you want to actually offer availability first, because at this point, this question asks availability. You want to be available in that particular area. So we are asking ourselves a question: how many GNODBs do we need to meet capacity and coverage demands? So in this case, you're saying, if for us to offer a service in, let's say, an urban area or in a market or something like that, how many GNODBs do we need? So this is mostly guided by us doing some information gathering. What kind of mobile service will be offered? What kind of equipment as well will be used? Because again, it's interesting for us again to think of this from different perspectives. So again, with 5G as it is right now, yes, we have the common equipment that we can use to access the mobile network, like the mobile phones, right? Mobile phones, the Samsungs, the iPhones, and so on. Those can have chipsets built specifically for 5G networks. That is fine. But we also have uncommon devices that have been built again to access 5G networks. So, for example, in our case, in our lab here, we have other devices that actually have Raspberry Pis built with 5G modems on top of them. They still can access the network using a SIM card. And the aim of that particular device is to extend coverage to other areas where we cannot deploy some big antennas in indoor areas. So that is, again, a 5G node accessing a 5G network to offer coverage. So we have to think about all those scenarios. If you're talking about how many GNODBs, what kind of GNODBs are you talking about? Are you talking about small and big ones? Are we talking about other, maybe using Wi-Fi to extend 5G signals in a particular area as well? So all these are things that we have to look at when we're talking about information gathering and data collection. How will we offer availability? That is the question we are asking in this particular case. And of course, the primary question is how many GNODBs do we need to meet capacity and coverage demands? So again, beyond this, you also have to consider stuff like the deployment options. Are you talking about standalone? Of course, this has been mentioned earlier. Are we leveraging on 4G at the RAN, 5G at the core network? Of course, and then why? The question then is, why do we want to do that? Because in other instances, you've seen other operators going the opposite way, where they are doing so as to maximize the capacity you can get with the 5G new radio. They deploy 5G new radio on the RAN only, but still rely on the 4G core. Still possible, because in this case, we are saying the 4G core is still all IP based. So we can still carry out traffic from the 5G new radio and still pass it over to the packet gateways that we have in the 4G network. Still possible, because as long as you can get that data, because the standards, if you're looking at the evolution of the core network, there are a few things that are consistent. Still, on the N3 interface between the GNODB and the core network, we'll still carry data there using GTP. So it's still normal. You can deploy it on a core network that is 4G based or 5G based. But can we say we are going to use a 5G RAN to get the good stuff with the 5G network and then still based on the 4G core? So in this case, we're trying to say we are moving faster into 5G deployment, but still not aggressively overhauling our whole core network. And then in this particular case, the incentives again are different for the operator and maybe other entities that want to deploy the 5G network, either in non-standalone in this case. Of course, standalone is straightforward, everything is 5G from end to end. So again, with information gathering, this is the info that you'd want to have, and then of course understand what deployment options do you have. Of course, again, with information gathering, again, there's a bit more here, spectrum information. Other cases you can allocate it, other cases you can use 3G and 4G spectrum, they can be refarmed to meet capacity demands. That is the technical know-how, just getting more info on spectrum. Again, you can do some information gathering based on social and market research. In this case, you want to find out, again, as I mentioned earlier, you have to find out what is the service or the device penetration. So again, in 5G, we really can't be limited to saying we are only looking at device penetration from the perspective of a mobile phone only. Yes, when 5G was launched, probably in 2020, the devices were out of reach. That is a fact, because at the time, the cheapest device at a particular time was in the north of $500 for you to get a 5G enabled device at the time, 2020. But then now, the devices coming down with prices, it's easier for us to even acquire 5G devices less than $300 or even $50 to acquire a 5G device. But then again, do we have even other cheaper options? Can we have some Raspberry Pis that are 5G modules? Can we embed them into other antennas and then access 5G network? So these are the kind of, again, this is guided mostly by the potential use cases. Again, of course, things like population density will, of course, influence how do we plan to deploy the network. Things like socioeconomical activities, again, will come in. What is the purpose of this network specifically? I can give an example recently in the Olympic Games that are currently going on in France. I think Orange have built a specific network for the Olympic Village, a specific 5G network for the Olympic Village. So their use case in this case that they're thinking we'll have these athletes in this Olympic Village, all of them put here together. Can we have a network that is specifically suited for this kind of setup? So they're building that. If you think about it, then in that case, talking about a very highly dense occupational area, many athletes, many fans with their support staff and everything else, occupying a very small area, but they all need connectivity. So Orange came in and were able to build a 5G network completely isolated from the normal 5G network that they have for the city, but this specifically is set up to serve these particular athletes in the Olympic Village. So that will be actually interesting. That will be interesting in that particular case of talking about use cases and expected level of service to be guaranteed. So moving on again from information gathering, you can talk about RAN dimensioning. So you can talk about, now you have the info, you have info about the tech, the demand, spectrum and everything else. Now you want to find out like how can I then dimension the network? So in this case, you're trying to do estimates here. Yeah, you're trying to look at what is the coverage radius, what is the capacity of a single site, how many sites do I need at the end of the day? So you have all that good info that is guiding you. Now you're looking at how then can I dimension this radio access network? And you'll find me mostly biased towards the RAN, because I mean, that is where everything, if you're not able to provide availability, it becomes harder for us to dimension anywhere else. So you have to start from the RAN and then look at how can we do some good RAN planning and then move on to the other aspects of the network. So in this case, you're talking about the coverage radius. So the output you expect to get is, what is the coverage radius that I have to work with? Then of course, this also influences things like the power that you're going to use for that particular transmission. Things like that will also influence that particular decision. So I'll go over this again quickly. So single site, what is the site of a capacity of a specific site? Then of course, that will give you some intuition of how many sites do you need in a particular area. So again, here we are talking about RF simulation, RF planning, and then this is also borrowed from previous radio network planning and design activities. Because with RF planning, we're talking about, yes, we are saying you need this number of sites, but then now we're trying to find out if we deploy this site, this G0 B here, are we able to meet the capacity demands that we anticipate to meet? So in this case, it's expensive for us to go to the field and try and do some trial runs. That's expensive. That is the desired situation, but then it's expensive for us to go to the field and do that. So what happens in most instances is we have a situation where we do some simulation runs. So we use some simulation tools to simulate the kind of transition we expect to get if we have some certain parameters that we input into those simulation tools. So the same steps will be done in the 5G after you gathering all the info, right? So you have all the info that you need for that particular area of coverage. Then you do some simulation to find out that if I provide these site parameters like latitude, longitude, antenna height, the bandwidth, the tilt of the antenna, and the beamwidth, what kind of transmission or reception am I going to get from both ends of the G0 B and the UE on both ends? So you're able to do that kind of simulation, then you see where to adjust. So when you go to the field, at least you have some idea of what to do. So that is the third step. So you've done requirement gathering, you've done frequency planning, now you're doing RF planning. And then of course, cell parameter planning is the next thing. Now you're going to a specific cell. So you want to find info about this specific cell. You want to find out what are the neighboring cells can I put on this closer to this particular cell? What are the physical cell identifier can I use? What are the tracking area codes can I use, among other information? Now we move to a specific cell and plan that particular cell. So we have here a very process here that has been detailed here in terms of network planning. So again, this process is iterative. That is the most important thing to get from this presentation. This is a very iterative process. So you'll always find yourself coming back and changing a few things here and there, because at the end of the day, you want to be able to offer a very effective network that is able to meet the capacity, coverage demands, and of course balance the tilt on your side as an operator or as service provider in terms of a very cost-effective network. So you may refer to this when you're looking, but most of the stuff here already mentioned, and why they're important. So this is like a summarized process. So again, coverage planning, if you're going to coverage planning, we've already talked about this in terms of what it is. So I'll just go over it quickly. So in this case, talking about the cell radius, where we want to find out what is the effective distance a user can send and receive requests without interruption. So in this case, we're looking at the edge of the cell, right? So that is that is mostly the consideration. So because we know if we have a user very close to the base station, more often than not, they will have some reception. How about the one on the cell edge? And what is this cell edge? That is the answer you're trying to look for in this coverage planning. That's what you're calling the cell radius. Tell us the cell edge, right? So coverage planning, we have a few things that we have to consider. So that we must consider the reception sensitivity of mobile devices. Again, in this case, we have to consider different mobile devices in 5G, because they are not, some of them even static devices in 5G. Again, are they mobile, are they static? We have to consider all that. We have to consider path loss, we have to consider transmit power, and of course, you have to consider link budget. So in this case, you're talking about if you consider all the losses that we have in a particular area, because not all topographies are the same. Urban areas, rural areas are different. So if you consider the link budget of a rural area and the link budget of an urban area are different scenarios. Again, if you consider someone is moving, someone is stationary, it's a different scenario as well. So we have to do some link budget calculation analysis, consider all the gains, all the losses, then sum that up and figure out which is the reliable link budget for us to actually deploy our network. So all this more details of this are of course captured in more detailed courses that talk about, but this is something we must consider when you're talking about coverage planning. So beyond that, coverage planning, talking about the network layout must be determined. You have to also look at the network layout planning. The aim is to look at out-of-cell interference, where you can receive signals from multiple cells. So you also have to look at those scenarios where we have a cell close to another cell. How do we prevent this out-of-cell interference? And then, of course, we have to consider the deployment area, which I think I've talked about, the urban, peri-urban, semi-urban, or rural areas. All this come into play, talking about coverage planning. And then, of course, a few things we have to consider when we are talking about coverage planning. We have to look at definition of the available spectrum that is used for a particular transmitter site. And then, of course, something that is important again for us to look at whenever talking about coverage planning is the capacity, the 5G capacity that will be defined for a particular area. And then, of course, will be guided by a few things here again, the design of the antenna array. So at this point, you have to ensure that the coverage and the capacity demands on the area are met. And of course, you may ask yourself a few questions like, how much gain do you require for a particular area? And if that is the case, can you employ things like multiple MIMO in that case? And if that is the case, again, can you think about beamforming in certain situations? So if you have info about some bias in a particular area at a particular time, can we say at 7 p.m. to 10 p.m., we have everyone at home, and if you look at this area, everyone is concentrated in a particular region, that is where they stay. So instead of us directing our beams to the roads where no one is at that particular moment, can we direct our beams to the areas where they stay? Yeah. Can we consider directing our beams to areas where they stay? So that is things that you must consider. Am I still audible?
Yes, you are, Humphrey.
Okay, right. So I want to go into detail in these calculations here, but these are stuff that you may consider when talking about if you want to, for example, to calculate the carried power, you must consider all this transmit power of the desired station, gain and everything else. So this is info that you may look at, and then of course they're guided by the different stuff like the array of the antenna. But I share the slides as well, so you can have a bit more info on that. So on the other hand, of course, you have to, if you want to consider interference carried power, the equation can help you as well. But these are the different inputs or variables that you must consider, right? So interfering transmit station, interfering station, the power of the interfering station, the gain of the interfering station, space loss, different kind of losses, okay, are the stuff that you have to consider again for you to determine the interference carrier power. Again, we've talked about coverage planning in terms of looking at the antenna design as well. So again, do you want to vary the tilt of the antenna, in this case, to meet very specific demands, right? You can see in this case, you have a different receiver that is an uncommon receiver to what you're used to, like the mobile phone. These are the stuff you have to consider again if you want to do some network planning as well. So currently we have some antennas that can actually tilt they tilt the antenna in different angles using just software. So the antenna will tilt itself based on configuration. You don't have to go up there and tilt it yourself. So using software, you can tilt the antenna. And then, of course, this mostly is guided by the sector size that you have. What kind of sectors do you have? Have you defined your sectors, and how can you meet this coverage demands based on this kind of techniques? So we've talked about propagation modeling. I've tried to give some info. Again, in coverage planning, you can do stuff like propagation modeling, where same activities you are used to when you're doing 4G and 3G planning with the different models that we have in those technologies. Again, there are very specific models that we have in 5G propagation modeling that you can use. So all these different propagation models calculate based on these variables that we have here: the operating frequency, the difference between the transmitter and the receiver, the size station, the antenna height, atmospheric conditions, and whatnot. So we have models that have been built specifically for 5G scenarios. So again, if you're working with that in mind, you have to consider using those models if you want to think of deploying a particular 5G situation. So this just gives us a background into the free space path modeling, which I think is this where we're coming from. But then again, if you want to go deeper into specific 5G propagation models, there's a bit more info on that as well. I think this is just a background on what free space modeling is, just to get you started into understanding propagation modeling. So again, if you want to work with simulators, again, if you want to make it more effective, in this case, you can also include stuff in the software, allows you to introduce stuff like digital map information, which is important. In this case, you can have info about the actual map of the area you want to deploy the network. So this gives you info like what highways do you have, what river bodies do you have, coastal lines, vegetation, the area that you're going to work with. So all this is info that you can gather and push into a propagation modeling software, right? So all these are things you can push into that particular software. And the more that you push in terms of data, at least the closer you get to having a very, very close to accurate deployment strategy at the end of the day. And then, of course, the configuration files, there are a few things here that are technical. Propagation model, of course, which I specifically use for 5G. The equipment configuration files, these are technical info that you have to use, as they are, most of them are cast in stone, like the frequency band. But of course, a few things that are different are these areas that influence, of course, how you go about this. So propagation models, if you're working with them, you have to consider all this info. So there's some GIS software that are able to give you files in a very specific formats that you can feed into propagation models software for you to actually get some good analysis of how can you do some coverage planning. So I'll move again quickly. We've talked about this already. So what are the important factors to consider? We've talked about this already. The advanced antenna system, if you're doing RF in the coverage planning phase, of course, guided by the tech that you have, are you using TDD or FDD? Are you using the frequency band 1 or 2? Are you using carrier aggregation or not? Of course, you have to define your carrier, which is the carrier frequency you're using that you're going to use in this particular case. So I'll go over this quickly again. This is again on simulation and modeling of when you're trying to deploy or simulate your deployment of a 5G area, of a 5G network. So the modeler sometimes may require you to provide more info, like the traffic information that describe the type of service that you're going to use, okay? Other case, you may even provide info, but the output that expect to get in these particular simulations is what is the network throughput you're going to get despite the conditions that you're going to provide in that particular scenario. So you're talking about the maximum throughput, the peak throughput, the application throughput, and the average throughput. So it's important to consider all this because, again, remember 5G with the use cases that it has, this is the info that is very important for different use cases, right? This info is very important for different use cases. So some use cases may actually be very insensitive to throughput in this case. They may be very sensitive to latency. So you may find yourself having to think about this differently. Okay, so if you think about a situation where we want to deploy a latency sensitive application, so we really don't care about the throughput because we are sending very, very tiny files in the kilobytes range, but they cannot be on the network more than 2 milliseconds, for example. Now, at that point, we are talking about how can we reduce the latency of these particular packets to 2 milliseconds? How can we do it? So a few things that you can use with the 5G as it is now, you can bring applications closer to the core network or even inside the core network and add them as extra applications, which most people call as the mobile edge, the cloud services at the edge or edge applications. So the aim in this case is to serve this particular latency sensitive application. And again, that same network again can be used with other apps as well. So if you think about the concept of network slicing, you can have a particular slice specifically set up for this latency sensitive application. At the same time, we have other slices set up for normal applications that actually can suffer latency, but they need throughput. So in that case, we dedicate more capacity to those networks to those services that need high throughput. Can think of these VR, AR services, or not even VR, AR, streaming video, for example, may need high throughput, high data to be pushed, but then again, the latency is not really key in this case. So you can have a slice for that as well. And again, as it was mentioned, the slices can be configured differently depending on how you want to set up your network. You can have a slice where all the core network control functions are shared with all the different network slices, but we have a separation of the user plane functions, where we have a user plane function for each network slice, depending and deployed in different areas, depending on what you want to meet in terms of latency, capacity, and throughput demands. So again, all these are different considerations that we have to make. But then again, that is now beyond the simulation tool, of course. Those are the different things you have to think about after you've talked about how you deploy your network. So moving on, of course, we've seen this already, what 5G brings to the table, peak data rates, capacity, network efficiency, spectrum efficiency, and so on. You've seen this already. Capacity planning, again, we have to think of how do we consider throughput. We have to consider then we can increase capacity on network by, of course, reducing the noise, the SNR value, and of course, reducing the spectrum, and of course, increasing the spectral efficiency. So this is just an equation just tries to bring on board into how can we then increase capacity? What are the things you have to consider, right? So the area capacity throughput is the bandwidth that you have, the spectral efficiency, and the cell density. So if you multiply that, you have the capacity throughput. So a few things we can control, and 5G does very well to give us a bit of control is spectral efficiency. It does very well in spectral efficiency. And then, of course, depending on how we deploy a network, we can also work with the value of SNR here. Can we deploy less noisy networks where we have a very, very high SNR value, the ratio? But then, of course, the value of B in this case can be constant for us, because if you're talking about deploying a 5G in 3.5 megahertz band, 3.5 megahertz band, and you only have 40 meg as bandwidth to work with, but you still require high capacity. Again, you have now to think of how can I reduce the signal to noise ratio in this case? How can I deploy an efficient network with very, very low, with very high SNR in this case, because the ratio is normally a ratio, SNR is a ratio. How can I increase my SNR value but still use the same bandwidth to achieve high capacity? So these are the things that you may consider just basing from this question. Of course, again, you may consider things like carrier aggregation. 4G came with 5 carriers that you can aggregate for you to offer some good capacity in this case. But in this case, for us, we are 5G, we can talk about up to 8 carriers that you can consider for particular bandwidth. But then again, of course, if you're going to for high bandwidth, again, you have to forgo a few things as well, things like distance, okay? And then, of course, capacity planning, again, you have to consider, again, available spectrum, right? So you're considering if you're going higher on the FR2 bands, again, as I said earlier, you're talking about ultra small deployments, right? But then again, a very good capacity. If you're down to the FR1 bands, you have coverage, good coverage, but capacity will suffer, right? So again, this is things you have to consider there's something else to give in the network, in the capacity planning and network planning in 5G, something else to give. And then, of course, again, these are mostly guided by the use cases and the different scenarios you want to deploy the network. So again, this gives more info on capacity planning. How can you increase total efficiency? You can use TDD, time division duplexing. Again, it's interesting because the TDD actually in 5G, it becomes very, very interesting how the 5G radio frame structure does the uplink and downlink transmission, right? Which can actually increase spectral efficiency. It's very different from what 4G does. That is something that actually you can employ to increase spectral efficiency in 5G. Then, of course, we've talked about frequency reuse using MIMO antennas and beamforming to increase spectral efficiency. So as I was talking earlier, we use in 5G radio, we assign a single frequency for use for both uplink and downlink communication slots. Okay, so in FDM, again, symbols are dynamically available for uplink and downlink based on throughput requirements. That is what 5G radio actually does for us. It gives us a few advantages in terms of TDD communication in 5G. Well, in the frequency domain, you use the whole slot for transmission. So you may actually use TDD in this case. Actually, I've been in situations where you find a particular network deployment, for example, the one that we have is doing downlink. Downlink is doing downlink on TDD, but uplink is doing uplink on FDD. Actually, you're free to actually, depending on how the software has been designed, you're actually free to actually mix and match this. So we've talked about antenna array distribution. So we've talked about the MIMO, single MIMO, all the way to 4x4 antennas. We've talked about beamforming again, which you can use to increase capacity. There's a bit more info here in how you can use beamforming to increase capacity, of course. Focusing beams to a particular region, of course, that will, of course, increase our value of SNR in this case, because if you focus the beam in a particular area, what you're saying is you're getting very, very good signals, okay? Very good power, reception power in devices. But then again, the noise is reduced. But with 5G again, with 5G radio again, you can move the modulation depending on the channel state indicator, the CSII value. So if you realize if you're deploying a 5G network again, if you have very good reception, the modulation actually changes from BPSK. It can go all the way to 64 QAM, right? So depending on the reception of the device. So sorry, is someone speaking? Right. So I'll just continue. So in this case, as I was saying, for you to increase capacity again, depending on this technique of beamforming, you actually even be able to use the advanced stuff on 5G, like increasing the modulation scheme dynamically as you improve the signal to noise ratio. So beyond that, I think a few pointers to consider. Again, we've talked about this site selection criteria now. Beyond capacity planning, we've talked about this is now capacity. We talked about coverage, capacity, and site selection. We are asking a few questions. Are there existing sites that you can use? Do we select a fit legacy site to reuse, or we just do a green deployment? That is adding a new site. Is a site close to important or dense areas? We have to consider the intersite distance. We have also to consider backhaul, and also I forgot to add here front haul as well, right? Because Again, with the deployment option, you may find yourself considering even fronthaul before you even go to backhaul, if you are talking about disaggregating your run. And then, of course, you have to identify forbidden areas due to regulation and zoning restrictions. Those are the things you have to consider as well. Now, this is you selecting a site for deployment. Beyond that, now, if should be the final slide, now, what are the challenges then we are talking about when trying to deploy our 5G network? Of course, spectrum challenges is a problem, because again, that is limited to us. We don't have enough spectrum for us to use as it is. We have people now moving to either refarming spectrum that was deployed for 5G or 3G. For example, 3G, you can refarm some 700 megahertz spectrum to use for 5G, but then again, in that case, you're suffering capacity. So we have to, again, do a bit of balances here and there. So spectrum is a challenge, okay? Lower bands are good for coverage, but low bandwidth is available for us to meet capacity. But on the higher frequency bands, we are talking about high bandwidth, yes, but then distance is limited. With more distance limited, you're talking about deploying more devices in terms of the G node Bs and the on the run. With the G node Bs being deployed, we're also increasing our operation and management cost, because in that case, we have to deploy the G node B, provide for energy sources for it to use, security, provide for the different physical devices, processing devices that it must use for it to actually provide some 5G services. So that is spectrum challenge is actually it's a double-edged sword that you have to consider whenever you're talking about the planning and deploying a network. Of course, we've talked about beamforming. This also has its own challenges. Okay. So because you're talking about 3D beamforming, you have to consider again a lot of computations being done by the antenna and the antenna system. So this, of course, if you're talking about increasing this digital signal processing, you introduce things like delay. Okay, and if you introduce things like delay as well, you may also be in a situation where, again, with the higher digital signal processing, again, energy is supposed to use in that situation also rises. And then, of course, hybrid mobility network challenges. Again, we should consider all the collected legacy networks when we're deploying our networks. Okay, so we have to find out how then can we have 5G interworking with all these devices, because one of the promises of 5G is a multi-rat deployment, where you can deploy the radio access network in different devices or accommodate different devices on the 5G core. That is one of the challenges that we have to work with. So if you're talking about providing something else that is not a legacy mobile network radio stack, interacting with the 5G core, it becomes tricky. How will you manage that in terms of, first of all, in terms of security and even data communication? So the hybrid mobility is a good thing in terms of pushing the standard and pushing the technology to be more agnostic to different technologies. Yes, but then we have to consider how then do we bring this together with the whole 5G network. And that is the end of my presentation. I hope I was good with time, Catherine.
Well, thank you so much, Humphrey. And thank you for going through over your deck. I know this should have been maybe half a day kind of webinar as a workshop, but we are very thankful and grateful to all the speakers for your different presentation. From an expert side, you have been very informative, and it's clear there's so much to learn about 5G. And here at Afrauti, we have a training on the same. Our head of training will be speaking on that as well shortly. But I know we promised you guys a Q&A session. So I'm going to have 2 questions from the chat section and 1 question from the floor. And I'll assign each speaker a question. So the first one, Mr. Mwenya, if you're still here, because this was asked during your session, what advice do you have for a wireless ISP startup for financing?
Wow, that's a very difficult question.
And keep the
What I
questions,
can just say,
the answers very, very short, please.
yeah, okay.
Yeah.
My advice, the business model for 5G is changing. I can see a lot of consolidation. I don't think we're going to have an entity called ISP in this arrangement, but I think you need to reimagine your business model to take advantage of 5G use cases and network slicing. you can still provide services without having a network. Martin was talking about cloud computing as one of the key technologies of 5G. So right now, infrastructure is a service, infrastructure is a code. There's so many cloud services which can be used by ISPs. So you just have to reimagine your business model. In fact, from a regulatory point of view, 5G is an advanced form of infrastructure sharing. So we don't expect to have too many operators. We just expect some consolidation, and the 5G should be a platform for service provision. It's like asking a question, should we build another Google when Google is a platform? Or let's say Facebook. Facebook is like becoming a platform. So what you can say is the regulators were just now trying to make sure that the monopolies, the platform do not monopolize. So from that point of view, I think you just need to reimagine your business model. I end it.
Okay, thank you, Mwenya. Martin, this goes to you. How can we use the maximum potential for IMT 2020 before moving to IMT 2030?
Okay, thank you, Catherine. I think I don't know who asked that question, but I think depending on the scale of deployments, I think it's a natural progression thing. It's not really the potential is, are we using it or not? It's a natural progression thing because the technology becomes available and so we use it. Now, some of the things that were initially envisaged for accommodation in later evolutions of the cellular technology for 6G, for example, they're already being deployed because there is, I would call it natural convergence. And to me, the biggest hindrance is how do we get commercial benefits out of it? Because if it doesn't make commercial sense, then it will not be deployed. And if you look at the nature or the state of deployment of even 4G across the world, while most Western countries, the Americas and Western Europe deployed, and China deployed 4G very, very fast because they saw the benefits from a service point of view, and they could make commercial sense out of it. They deployed them, devices were available and so on. And I think that question arises when we don't have the financial capacity to deploy the state of the technology, such that by the time the next generation of technology becomes mature, we are still deploying the previous one, which is a case that's happening to most of Africa. We are only 35% covered by 4G. 5G is already here. We are less than 5% in Africa. But to me, I think what we need to look at now is service provision rather than the technology that we are offering. So if we can provide the services that are required, at the most efficient evolution of the technology, then we should do it. And when the older technology can no longer sustain the customer demands, we move to the next one. That's why, for example, I see that 3G will be switched off everywhere around the world way before 2G, because irrespective of what it is, there are still some applications that 2G is doing that 3G can't provide, and what 3G can provide has already been superseded by 4G and 5G. To me, it's that we should apply the right technology to provide the right service or the service that the customer requires. There's a lot of convergence. So 4G, 5G, can deliver pretty much almost the same services, and therefore we should not really spend a lot of time looking at the generation, not unless there is a new demand that the previous generation cannot offer. And that's what I have to say to that one.
All right, thank you, Martin. Do we have any question for Humphrey from the floor? Any question for Humphrey? Silence, I'll take. Okay, go ahead, Kosi.
Okay, good afternoon. I'm sorry. We don't finish to check the performance of the technology we are using now, like 3G, 4G, and now we need to move to 5G. How that can be a big challenge in rural area, for example, where we don't have any kind of technology.
Okay.
There.
We can have Humphrey answering that.
You know, Anita.
Let us know.
Anita.
In the rural area, what is the challenge? In big town like Abidjan, Cotonou, Lagos, Abuja, and so on, we can know people needs to have quick using experience when.
Okay, Humphrey.
But in terms of for everyone, and in terms of team, we need it for farmer in rural area. What is the challenge? How can we?
All right, thanks, Kosi. That's an interesting question, and actually it provides a bit of background into why, if to answer the question why 5G. So I'll answer it in two parts. So the first part is you are a very interesting use case. So you're talking about the rural areas, and you want farmers to be able to get access to connectivity. And in this case, you're talking about fast connectivity. So again, in this case, fast will be relative to what kind of application they want to use in the farm. Okay, that will be carried, of course, with what kind of technology they want to deploy on the farm, what kind of, let's say, control mechanisms they want to use the farm equipments, or if they want to do things like farm surveillance and whatnot. So the question there will be, how can we define that use case in a farm in Abidjan and a farm in Kenya, or even a farm in South Africa? So these are different use cases and different demands that we can get from that one use case of a farm. And on the other hand, to answer the other question where we are moving from 4G, 3G, 5G, we haven't finished testing 5G and 4G, and now moving to 5G. I'll ride on what Martin talked about. It will get to a point, this is not my personal opinion, to get to a point where the Gs will no longer be important, really, because the generations of mobile communication is less like routine, being done every 10 years before we get another standard out. So we expect the other one, 6G, to be out by 2030, and of course, early before 2030, we can get the standard out and maybe deployments in 2030. But then again, the thing is, if we move from the G deployment, right, then we now talk about just mobile networks. The question then normally is, do we have, first of all, connectivity in that area? Do we have access to the internet? Because if everything is going to the internet, the question that we normally ask is, do we have, first of all, have internet there? So if we have internet, a point of presence of internet in that particular area, then now we can now provide wireless services to suit our needs on the other end. And these wireless services in this case can come in the form of the different technologies that we have, 5G being one of them, through stuff like deploying private 5G networks in this case. And then of course, that of course will be guided by us having wireless services. And again, I can just bring you some other perspective as well, where right now in the 5G deployment world, and of course, moving back a bit to the 4G deployment, we now have access to even open source software that we can use on just normal hardware devices for us to test these services. So in the near future, it will not be very hard for us, even in a small setup, like a small test environment, for us to have very cheap, in this case, relatively cheap equipment for us to test 5G, because we have open source software that is allow us to emulate 5G radio access network, the full stack from the PDCP layer down to the physical layer. We can emulate all that. on just a normal general purpose hardware device. So it has small antennas you can use. On the other hand, you can also deploy the core network with all the network components from the SMF, AMF, UPF, all of them with the service-based architecture down to a very, very small device. A Core i5 is able to host a core network for you, a Core i5 device. So in the future, the future looks bright because with the open source tools that you can use for different test beds. But then again, do we still have connectivity coming in for us to get internet access? Now you're talking about the other interface connecting to the internet beyond the 5G network. So that is my take on that question.
Thank you, Humphrey, Kosi, and to the rest of the delegates present. I know you have more questions and you'd like the speakers' inputs. I'd encourage you to link up with them on their LinkedIn platforms or pages. But we are also, as a faculty, going to share all the presentations that have been presented today. And we can also share emails to the respective speakers. At this time, I'd like to invite Mr. Jonathan Makijele, our head of training, to give his closing remarks. Welcome, Jonathan.
Yes, thank you very much, Catherine. Yes, I hope you're able to hear me.
Yes, we can hear you and see you.
Oh, fantastic. That's great. So thank you very much, Catherine, for moderating this webinar. It was really great on 5G mobile networks. And for sure, as you said, I think we needed maybe, is it a half a day? Maybe would have been sufficient, at least 3 to 4 hours. Again, thank you very much, Anita, who coordinated this specific webinar. Thank you very much. Again, for the speakers, Mr. Mwenya, Martin, and Humphrey, we appreciate. Thank you very much for your time and your commitment. I know it was a short notice, but you are able to prepare something. So I appreciate also, especially Mwenya, talking about issues of 5G mobile standards and the regression, and your experience working as manager at ZICTA, and also spending some time as acting Director General of ZICTA. So I think the experience of Zambia and also sharing the experience of Zambia, I think that was great. Thank you very much. And for Martin, I know there's quite a lot talking about 5G mobile technologies. For you, I think you needed a full day by yourself. I think there was quite a lot of technologies about 5G. So thank you very much, Martin. And for Humphrey, yes, I think talked about 5G mobile planning and a little bit about deployment. We appreciate. Thank you very much. And yeah, so for the trainees, for the participants, I just want to let you know that yes, we have spent at least like 2 hours plus. Yeah, but at least now you appreciate, how rich the speakers are in terms of content as far as 5G mobile networks is concerned. So I would just encourage you, be in touch with myself, be in touch with Anita, and of course, even the speakers with regard to anything with regard to 5G mobile networks. Yeah, so we have developed at least 2 courses. One talking about 5G mobile technologies, the emerging and new technologies been covered there. And, so we have Mr. Martin Mwaura, is an expert in that area. And I know we have supported Communication Authority of Kenya here and many other AFRATI member states. So you're welcome to ask for more information. We'll be able to share with you. We can do in person, we can do also online. Then this year, I think the beginning of this year, we also developed a course talking about 5G network planning and deployment, of course, which was delivered by Martin and also supported by Humphrey. So you're welcome to subscribe and ask more information about these 2 programs as far as 5G is concerned. So some of the courses we offer in partnership with ITU as one of the ITU academic training centers. We do also work closely with them. Yes, so we can offer as a fratty, or we can also offer jointly with the ITU. And I understand the majority of the participants were coming from the cause and the role of standards and interoperability. So thank you very much for creating time to be part of this, and also others joining from our member states and the rest of the continent. We appreciate for you creating time to be able to join. Yeah, so just in case if you need more time, more engagement, maybe I will try to find the availability of the facilitators next week on Thursday, but I know Mwenya will be there because he'll be taking you through issues to deal with the role of standards and interoperability, and also sharing different case studies. So just in case Humphrey and Martin will be available, maybe I'll ask them also to join, so that in case you've got specific questions on 5G mobile networks, you can be able to ask. So at this juncture, I just want to say officially this workshop or this webinar has ended. So thank you very much all for your participation. And again, as shared by Catherine, basically all this presentation will be available to all the people who were able to connect today. So thank you very much. Back to you, Catherine. I'm not sure that Anita has got any announcement to make. Thank you.
Thank you, Jonathan. Anita, do you have anything else to add on?
Thank you so much, Kathy, and thank you, Jonathan, for giving the vote of thanks. To the participants, we really appreciate your time and your active participation in this forum. I don't have much to say. It has been said by Jonathan. All I wish you all the best. Thank you so much, and back to you, Kathy, to close the session.
Okay, thank you to all the speakers, the delegates, my colleagues from Afralty. Thank you all for making time and staying till the end, really. I know we pushed over, we promised 2 hours, but we've gone over that, but we still have some of you here. We do not take that for granted. We'll continue engaging you on our various platforms, on our social medias, our emails. You can reach us directly if you have our phone numbers. We are happy to provide more information, and if you have any other inquiry that you might need from Afralty, we are happy to assist. I will call the meeting the webinar to a close, and I wish you all a good evening. And I know some of you, it's afternoon in your various countries. I wish you a good afternoon and evening and day. Thank you so much. Goodbye.
Goodbye. Thank you, Kathy.
Bye-bye, thanks.
Thank
Goodbye.
you. Goodbye.
Thank you.
Thank you.
Thank you.
Goodbye.
Goodbye.
Bye.